thank you everybody. Welcome for joining. Apologies for the link issues that we had. I think people will be streaming in over the next couple minutes, but I'd like to welcome everybody here from Microsoft's team. It's a great honor, Rich. I'm so happy, so pleased that you have taken the time to do this, and obviously with your team as well. We're really looking forward to it, and obviously for your talk as well tomorrow on the platform, the conference. So thanks everybody for joining. I won't delay any longer. I'll let Rich take the stage and enjoy the workshop here. Thanks, guys.
That's great, Dave. And I think we see your daughter in the background, so hopefully she'll be joining us as well. So. Hey, so we might as well get started. I think some people will be joining us late. Hey, I'm Rich Caruna, machine learning researcher at Microsoft Research. The four of us are all from Microsoft, and we all work in intelligibility explanation for machine learning. So we've structured this as a tutorial, and the way we're going to do it is Marco will start off by giving an introduction to explanation in machine learning. And then he'll also talk about LIME. Marco is the inventor of LIME, a very well-known system for interpretable machine learning. And then after Marco finishes, there'll be, maybe 5 minutes for questions. So you'll be able to type questions into the chat for Marco. And then we'll switch to Scott. Scott's the inventor of SHAP, another very well-known system for explaining machine learning systems. So Scott will talk about SHAP, and game theoretic approaches to explainability. And then there'll be another 5 minutes for Q&A after that. Then I'll talk about glassbox machine learning systems that are designed to be interpretable as opposed to explaining black box systems. And we'll do Q&A after that. And then if there's 15 minutes left at the end, Harsha is going to do a demo of an open source system we released a couple of years ago that ties all of these things together, that lets you use LIME, SHAP, and the generalized additive models I'll be talking about all in one user interface. So anyway, thanks for coming. Hope you enjoy the tutorial. Feel free to ask us questions in the chat. We'll try to get to those in between talks. And if for some reason we can't answer your question, we're all happy to have you contact us, offline, and we'll do our best to talk with you then. Okay, I'm going to hand it off to Marco now, who's going to give you the introduction on explainability and tell you a bit about LIME.
Thanks, Rich. So you guys can see my slides and hear me okay.
Yes, everything looks good, Marco.
So yeah, I'm just going to do the intro, basically answering the question, why bother with explainable AI? And Rich and Scott and Harsha will go more into the details. So let's get right into it. If you take a machine learning course, and like in grad school or even undergrad, you'll learn that machine learning is this magic process that goes something like this. You get some data, you train a model, nowadays a deep neural network. Then you get some statistics like accuracy on held out data. And if they look good, boom, you can power a product and machine learning solves all of your problems. This is a common caricature, but there's something crucial missing from this picture that people often forget. And I'm not necessarily talking about the huge amount of money that you make with machine learning, although that is also missing there. What I'm talking about is humans. So in this process, it looks like humans don't matter. It's just a matter of getting the right data and then training a model and boom, you're done. When in fact, humans really matter, and humans want to communicate with the model at this multiple steps of the pipeline. So the first kind of human that we have here is the machine learning person. So they're training a model. They have to decide, what model should I use? What feature should I use? Is my model actually working? Can I trust the statistics? Am I going to get fired? You also have the business of or product person, the PM, if you say. So the PM is thinking things like, should I trust this model? I know that the machine learning engineer likes it, but is it going to get me fired? Is it racist? Is it going to lose us a bunch of money? Does it actually work? You also have the end user. So not in the case of Siri, but if you're developing a system that's going to aid doctors, for example, in doing diagnosis, or judges or whatnot, the end user has to decide, okay, this machine learning model is telling me to do X. Can I trust it? Why did it say that? Like, there's no way that a doctor is just going to open up a patient just because the model said so. So you need this kind of dialogue to happen. And then finally, you have lawyers that may require this communication to happen. Like, for example, in the European Union, you're required to provide explanations for algorithmic decisions. And there's more people that I didn't list in here. This is just a sample of the kinds of humans that matter in this whole machine learning process. So where do explanations come in? Here's a dictionary definition. To explain is to make something clear to someone by describing it in more detail or revealing relevant facts or ideas. And what we're making clear in this case is a model or its predictions. We have a model and understand what it's doing. The someone, I already said, it really depends who the someone is. So there's a bunch of different stakeholders who may want to understand what's going on or get things cleared up. To make it clear, as I said, requires some communication. So I drew a funny telephone in there where you have communication going from the model to humans. And then we have this part of the definition that says describing it in more detail or revealing relevant facts or ideas. And in order to decide what is relevant and what the appropriate level of detail is, we really need to think about the purpose. Why are people using explanations? What questions are they asking? What are they trying to do? What are they going to do after they see explanations? And this question is crucial for us to decide what a good explanation is, whether we want explanations or not, and so on. Given a purpose, you have what I'm calling explanation type, which is what people actually see. What do you tell them? How do you display this information to them? And we're going to walk through various explanation types. And then finally, once you have a purpose and you have a desired explanation type, there's technique. How do you get from a model to this explanation type? So these three axes, as it were, are going to form the basis of my talk. And I think it's a good framework for how to think about explanations in machine learning. So this should be useful for the rest of the tutorial. And if you in the future encounter any papers or talks on the subject. So here's a cheat sheet: purpose, explanation type, and technique, and we'll go through each of them in turn. Starting with purpose, there's many reasons why people want explanations, but I think they can roughly be categorized under three headings. So we're answering the question, what are explanations for? And I think there are three headings. The first heading is to augment humans. So here I'm going to draw an axis from general to specific information needs. So all the way on the general side, you may have a doctor saying, hey, how do I diagnose this disease? And this heading says augmenting humans because in the end, the human is the one making the decision. We're using a machine learning model to help to make suggestions, to get insight, but the human is the one who is actually performing the task. So human is actually doing diagnosis. We're just using a model here to get some insight or maybe get some features that we should be looking at or something like that. And that's a very general information need. All the way to specific, you can have maybe a diagnosis of a specific patient. What is wrong with this patient? Again, same thing, the doctor is making the decision, but now it's a specific question we're interested in, Mary, as opposed to the disease in general. And just to add a twist, what if Mary is bleeding? It's the same patient, but the level of detail that's appropriate now is different. If you have a patient in the operating room, you want probably something that can be grasped at a glance rather than something that takes you 15 minutes to parse and think about. Same thing with a judge. Should I grant bail to John? That's different than how do I decide how to grant bail? It's a more specific question. And less high stakes, whenever you get a recommendation from Amazon or Netflix, you have to make a decision, do I trust it? And you are deciding, do I watch this movie, do I buy this book? And the system is just trying to augment you by giving you suggestions and helping you and so on. And in this case, explanations can help. This is the first heading. Second heading is when you're helping humans evaluate the AI. So you have a model or an AI, and you want to ask, can I trust this? Should I use this diagnosing system? Should I use this thing to help judges grant bail? Should I use this system to optimize click-through rates? Can I trust this? That's a basic question where explanations can help. A little more specifically, you may have specific questions like, is it racist? That's more specific than can I trust it? Or all the way on the right, you may want to explain every prediction, maybe due to compliance reasons. But in terms of evaluation, for example, if you make lending decisions, one way to evaluate that is to say you have to explain everything so that people can sue you if you use protected attributes or something. So this is the second heading. Third heading is when you're helping humans improve the AI, and it's directly related to the second one. Once you evaluate if the model is lacking something, you want to improve it. And explanations can help you figure out how to improve it. Like, what kind of data should I get? If you identify that the model is struggling with a particular kind of data, maybe that's the kind of data they should be getting. Or maybe do I need to change model architecture? So if you realize, hey, it's not the data that's the problem, it's that my model is not flexible enough to learn the pattern that I care about, or that my model has an inductive bias that's hurting me in some way. Or maybe more specifically, you find a specific bug, like this was a famous case where if you Google the name of a Harvard professor, Google would give you all of these things about being arrested and records because her name, I guess, sounded African American. Once you find this terrible bug, you want to know how do you fix it? And in order to fix it, you have to figure out where it's coming from, and explanations can help. So these are very different information needs. These are different purposes, different questions in terms of general to specific. Thinking about this really is crucial when you're thinking about explanations. You see many papers and explanations that just assume one purpose. So they'll talk about explanations, assuming that what you want to do is evaluating the AI, or assuming you want to augment humans, or even assuming that you care about one specific type of human augmentation, like very specific questions. But that need not be so. So you need to think about, why do I want explanations? Once you figure that out, then you have a menu of explanation types to pick from. I'm going to use as an example income prediction. Let's say you have some census data and you train a model to predict whether people make more or less than 50K. It's just a toy problem to illustrate the kinds of explanations that exist out there. So explanations, again, from general to specific. I'm going to give you a sample of different explanation types. So one way of explaining a model is to just tell people, here's what the model is doing as a whole. So if you have a very short decision tree, for example, you can say, this is the model. And you can grasp all that it's doing immediately. This model is saying, if a person has college, I think they make more than 50K. Otherwise, I just look if they're older than 40. If so, more than 50K, otherwise less. And you can understand everything about the reasoning process immediately because it's a very short and compact model. So this is a whole model explanation. And this is very general because you can answer any questions about the model you want with this kind of explanation. You just have to look at it. Another kind of explanation is what's called feature importance, and this is global feature importance. So this is saying these features are important for the model when making decisions. Now, it's not telling you how they're important. It's not telling you how they're being used. It's not telling you what kind of job types are important, whether education is positive or negative, whether there's interactions between education and capital gain. It's just telling you these are the important features. So this is also very general, but allows you to answer different questions. Another kind of explanation is what's called a partial dependency plot. And here it's a little more specific. You're looking at one feature on the x-axis and you're seeing how the model prediction changes as you vary that feature, either counterfactually or in your data set. So this gives you an insight into, like, in this case, for example, we're saying that as education goes up, the model predicts that more people make more than 50K, which makes sense. So this is a partial dependency plot, a little less general, more specific. Another kind of explanation is to just slice the data in different ways. So instead of getting statistics like accuracy, you say, oh, how does my accuracy for men compare to my accuracy for women? How does my accuracy for African Americans compare to my accuracy for white people? And you may want to make sure that those accuracies are paired, or if not, you may want to understand why that is. So that's the kind of explanation that can be helpful. All of these are general in the sense that they're talking about the model as a whole, rather than looking at a specific prediction. But if we have a specific individual in mind, like Bill Gates, in this case, Bill G, to preserve anonymity, and let's say that my model makes a decision or a prediction that says Bill G makes less than 50K, and I want to understand why. This requires a different kind of explanation. It doesn't require, but you can get this information with a more specific type of explanations, which I'll be showing now. So that's why I had cross in there to separate explanations that are general from specific predictions. So one kind of explanation was called an anchor. And it's saying, look, if you take BUG's features, here's what's sufficient for a prediction. Meaning, if someone does not have a college degree, the model always predicts less than 50K. The rest of BUG doesn't really matter because this is enough to predict less than 50K. So this is an anchor. Still a little general because it's easier to apply this to other people that don't have a college degree, but it is coming from BUG specifically. Another kind of explanation that's very popular, perhaps the most popular for this kind of explanation, specific predictions, is a local linear model. And this is giving you a list of pros and cons. What those weights mean differs between methods, and Scott maybe will touch on this. But the point is that you get a list of pros and cons. So BUG does not have a college degree, so that's a con. He works a lot, that's a pro, but he is past retirement age, maybe that's a con. And this gives you insight as to how the model is making decisions. It's more specific because it's hard to figure out how to apply to other examples, but it's still useful. There's also what are called counterfactual explanations, which change the original input in such a way as to change the prediction. So this is saying, look, if you add college to BUG, the prediction changes. It doesn't tell you whether adding college will change other individuals. It doesn't tell you more general information, but it does tell you, hey, BUG, all he needs to do is to get a college degree and then he'll make more than 50K according to this model. So this is a counterfactual explanation. And then finally, there's what's called influence of training examples or influence functions. And this, instead of explaining in terms of BUG's features, this is looking at the training data and trying to find examples that influence this prediction. So this is saying, look, I'm predicting that BUG makes less than 50K because he's similar to this other individuals, and you have to go and figure out how. So this can be really useful for debugging the training data and stuff like that. This is influence functions. So someone should probably mute themselves. I hear some background noise in there. Anyway, we have all of these kinds of explanations here. Which one is the best? And if you've been paying attention, you know that the answer is, it really depends on what you're trying to do. If you're trying to, for example, if you're a sociologist and you're trying to figure out what are important predictors of income.
Hey, Dave, are you there in the meeting? And if so, are you able to do a mute all for us?
I think maybe we as co-hosts can mute all. Let me try. I'll take a pause here. Mute all. Okay, I think I did it. Cool. Yep. There we go. So if you're a sociologist trying to predict important predictors of income, figure out what's important when predicting income, then maybe what you want is a feature importance explanation, because that's precisely what it's giving you. What are important features? It's not telling you how, but what's important. Now, if you're trying to figure out, is my model fair? Then depending on what you mean by fair, what you want is slice statistics. You want to figure out, does my model work as well for African Americans as it does for white people? Then you want slice statistics. If you want, you could also use other explanations, but in this case, maybe what you want is this. If you're a BUG and you're trying to figure out how do I make more money, then maybe what you need is a counterfactual explanation. More seriously though, if your loan got denied and you want an explanation, probably what's most useful is telling you what could be different about you so that you can get your loan approved, rather than telling you, hey, here are people who look like you. So it really depends. And that's why I had the whole section on purpose, because instead of saying this explanation is better than this one, you have to figure out how are you going to use it and which one supports my purpose. So that's explanation type. Lastly, I want to talk about how you get this explanation, so technique. So let's say that you want to interpret machine learning and you want a local linear explanation. How do you get that? There's basically two camps. Of course, it's not as black and white in this, but there are basically two camps. One is to say, let's use interpol or glass box models. Another one is saying, let's use black box explanations. So Rich would fall in the first camp mostly, and he would say, let's train a glass box model. So he might say, hey, you want local linear explanations? Let's train a model that produces local linear explanations. He probably would not say linear model. He'd probably say, let's use a gamma or something like that. But the point is that you train a model that is able to deliver the kind of explanation, the explanation type you want. Whereas me and Scott would probably say, just bring whatever model you're using, and we'll come up with techniques that can generate this kind of explanation. Now, obviously, there's a trade-off there. There's multiple trade-offs. If you're going the interpretable model route, typically your explanations are exact. They're not approximations. The model is doing this by construction, and it's also fast. But if you're using black box explanations, typically for some domains at least, the models that you can use are more accurate. And also it's more flexible in the sense of if you want to change models, you can use the same explanation. Or if you want to change explanations, so if the person says, hey, I want an anchor instead of linear model, interpretable model camp would have to say, let's train a different model. Whereas our camp, black box explanations, would say, sure, just bring your model and we'll explain it. So there are trade-offs. I'm not saying that one is better than the other. It really, again, depends on the purpose. If you need exact, fast explanations, or if you can get away, like if an interpretable model is accurate enough for your domain, that may be preferable. If you need more flexibility, then maybe you want to look at black box explanations. So for example, if you're a doctor or if you're in medicine and you want to figure out how to diagnose patients, probably better to go the interpretable model route. I would not trust a black box model to do this, even if we could produce explanations. Anyway, there's also a trade-off, as I just mentioned, between accuracy and interpretability, and this is not a scientific figure. It's just what tends to happen. If you want a model that's very interpretable, it tends not to be very accurate. Like a linear model or a decision tree, they're easy to produce whole model explanations or linear explanations with those, but they're not very accurate. And to make them more accurate, we make them less interpretable by adding a bunch of features or using random forests and so on. Now, Rich does a lot of research on interpretable models, which means we can get all the benefits of interpretability while maintaining accuracy, and that's great. For some domains, though, we're not able to reach the desired accuracy yet, in particular for vision and NLP, that's the case. Although for tabular data, they've had great success. Whereas deep learning or ensembles typically have pretty good accuracy even on these domains. Sometimes even as good, it seems, as humans, typically not though. But so being model agnostic or getting black box explanation means we're going to ignore the model internal structure and just assume it's a black box. So as I said, we can explain any future models, any existing models, and we can compare models and so on. So this is good. This is saying let's shift everything to the right, which has its benefits. However, interpretable model research is trying to shift everything up, which is also great because often these deep learning models have very high accuracy by using shortcuts. So if you can get very high accuracy of interpretable models, it tends to be more real accuracy, meaning it generalizes better. So again, trade-off, you have to figure out what makes sense for your domain. So technique, two main camps. Obviously within each camp, there's a lot of different techniques. I'm just going to touch on one. I'm going to touch on LIME, which is a technique that I developed in 2016. And the reason I'm touching on LIME is not that I'm saying, oh, you should be using LIME necessarily. It's just that the principles involved here apply to a lot of black box explanation techniques. So it's good to understand how this one goes. And LIME is also very simple. So LIME, for LIME, we're explaining individual predictions rather than explaining the whole model as a whole. So if you take this 2D figure I have here simulating a very complicated model, the global explanation is too complicated. I basically have to give you the whole model for you to understand it. But if you zoom in to that X in there, let's say it's Bill Gates, if you zoom in enough, the model looks pretty simple. Like it looks linear. It's a linear model close to Bill Gates in that case. When that's the case, you can explain it like that, such that the explanation is locally faithful. The explanation is telling you what the model is doing around Bill Gates, even though it doesn't tell you overall what the model is doing. So an explanation looks like this. So here's an example where we're trying to predict whether an email is about atheism or Christianity. We train a model that has really high accuracy. You may think this model is good, but if you look at an explanation, it looks something like this. So here's an email that's saying Christianity is true, blah, blah, blah. It's clearly about Christianity and the model makes a mistake. The explanation is a local linear model, like I said before. It's a list of pros and cons. So it's saying Christianity is a pro towards Christianity. but posting, host, and Keith are pros towards atheism. And if you look at this explanation, it becomes clear, hey, this something fishy is going on here because Keith, posting, and host have nothing to do either with Christianity or atheism. So if the model thinks that they're important, something is off. And if you dig a little deeper, you figure out that this data set has this shortcuts. So Keith in this particular data set appears in 11% of the training data and validation data and test data, always in the class atheism. Obviously, this is not going to generalize, but it helps you inflate accuracy for this particular data set. So this is just an example of what an explanation looks like. This is how we get these explanations in a nutshell. So the idea is we don't have access to the model internals. So what we're going to do is we're going to sample points around Bill G. So we sample a bunch of points to perturb Bill Gates in various ways, and we sample examples, and then we get predictions from the black box model. So we get whether they're positive or negative, and then we weigh those samples according to how close they are to, in this case, Bill Gates. So we're saying if someone is very close to Bill Gates, we want our explanation to be very faithful. If someone is completely different, we don't care as much. And then we learn a simple model on these weighted samples and use that simple model to explain. So we learn a linear model and explain it with that. Now, I said we learn a linear model, but we have to talk about what the representation for that model is. So even if the black box model uses something like embeddings that's completely uninterpretable, we still want to perturb and explain in terms of something that people can make sense of, like words. So we call this an interpretable representation, and this is what we perturb it and explain. So for images, instead of using 3 color channels per pixel, maybe we use contiguous superpixels that we turn on and off. And I have an example right here. Let's say we want to explain this prediction, Labrador probability 21%. The way we perturb it is we hide various superpixels, and then we get a prediction. What's the probability of Labrador? And if you hide everything else, if you hide the guitar, the model likes the Labrador because it sees the dog's face. If you hide the dog's face, it doesn't predict Labrador as much. And you do this again and again until you get a data set. And then you weigh that data set according to how close it is to the original image. So the more you hide, the further you are. And then you produce an explanation from that. Basically, that's saying the dog's face is really important for a prediction here. So this is an example of sampling and perturbing. Now, I've been talking about explaining an individual prediction, but we may still want to get an idea of the global behavior of the model. So if I explain Bill G over there, I'm only getting a sense of that part of the input space. What if I want to understand more? So obviously the user can't examine explanations for all data points, but we can maybe pick a few in a smart way so that they get a good picture. So we're saying that the set of examples we pick must be representative and diverse. So if we have those 2 examples there, they're very close, but if we have the green one, it's different enough that we want to pick it. And how we do this is via submodular optimization. It's a very simple procedure. We're not going to go into the details. I just want to make you aware that there are techniques to pick different explanations, even if they're explanations for individual predictions. So LIME is specific questions. It's a local linear model, and it's a black box technique. So that's how you think about it in terms of this cheat sheet. Purpose really comes in when you think about evaluation. So if we're doing experiments, the first thing you should ask about is, what is the purpose? What are you trying to do? And we did experiments in evaluating the AI and improving the AI. So evaluating the AI, we had this fun experiment where we told people we trained the model to predict wolf or husky, and we showed them different predictions, where in reality, even though the model is very accurate, we only train the model to predict snow or not. So if there's snow, the model predicts wolf, otherwise it predicts husky. And it gets high accuracy because we constructed the data set that has this bias in it. So the question you're really interested in is not in this model, but it's on whether people notice this. And by people, I mean machine learning PhD students or professors. So we ran this experiment where we showed them predictions. We showed them 10 predictions, and we asked them, hey, would you trust this model? What do you think the model is doing? Like, how is it making predictions? And then we showed them explanations and asked them the same questions. So the idea is, did people get the insight? Like, the insight is clearly there if they pay attention, but do they notice it? Here's the results. Before explanations, 60% of people did not trust the model yet. after seeing 10 examples, which is good, but 40% did. And we also measured how often people listed snow even as a potential feature. How often did they get the insight, even if they mentioned other ideas? And less than half of our participants got the insight. Instead, people made up all sorts of reasons like, hey, I think the model is looking at the teeth or the wolf's eye, or the wolf looks more aggressive or something like that. After seeing explanations, almost nobody trusted the model and almost everybody got the insight. So explanations really help even experts, even in a toy example like this. And this, I think, generalizes because when you train a model, you kind of want it to work. So it's easy to make up stories and not evaluate it properly. But once you see explanations, it really helps you get this kind of insight. So that's evaluating the AI. In terms of improving the AI, we had a couple of experiments. One, we're getting Turkers to do model selection. So we're showing them two models side by side with explanations and asking them, which model do you think is going to generalize better? So we're measuring how often do they pick the model that generalizes better as measured on a different data set. If they just guessed, they would have picked the right one 50% of the time. With random Lime explanations, they get it right 75% of the time. With the smart procedure that I described before, where you're picking explanations to be representative and stuff, they get it right 89% of the time. So that's pretty good because these are Turkers. They're not proficient in machine learning at all, but they can still do model selection based on which model makes more sense. So in this case, we also had an experiment with fixing bad models. And here's the procedure. We have the original data set. We show people explanations and we ask them to click on what doesn't make sense. So they're saying, look, Posting, Host, and Keith have nothing to do with atheism and Christianity. Please remove these features and retrain the model. And we repeat this process a few times. And then we evaluate a model on a new data set that Turkers don't know about, so they can't be overfitting to that, to see whether it generalizes better. So here's the result. Here's accuracy on the hidden set. If you just train on the original data set, you get pretty poor performance, 57%. If you use a bunch of regular expressions to try to clean up the data set, like removing headers and removing names and so on, you get way better. And I came up with these regular expressions. So you get 70% basically. Here's what you get if you do this few rounds of clicking on explanations. You get even better accuracy, pretty good accuracy, almost 75%. And this is pretty cheap. So each round of clicking on features took an average of 3.5 minutes. And I think we paid people like 50 cents or something. So for $1.50 and 10 minutes of work, you on average get a model that generalizes much better, even using this very rudimentary form of feature engineering. Like if you think about what else you could do, you could get more data and so on. The idea is that probably you can fix models way better. And these are Turkers. Again, they don't have any expertise. So improving the AI, at least for the particular case, was what we're trying to achieve. Anyway, this cheat sheet, I think, is helpful. Stepping back from Lime a bit, whenever you think of a model, an explanation technique, Lime or otherwise, I think this is a useful grid to think about. What are we trying to do? What are we showing people? Does that support what we're trying to do? How do we get those explanations? Do we do interpretable models? Do we do black box? In this tutorial, Scott is going to talk about another black box technique, SHAP, and a bunch of applications. Rich is going to talk about different interpretable models. Harsh is going to have practical details on how you even run this, what kinds of visualizations you have, and so on. But I thought it would be useful to start with this grid to get you thinking, in my view, in a good way about what we're trying to do here. And that's all I have as far as presentation. I'll take a look at the chat to see if we have questions there, and feel free to ask more questions there as well. Let's see, I'm taking a look at the chat now. Okay. So whenever dealing with models based on people, shouldn't we be applying any no gender, ethnicity, etc. fairness tests as a default? I'm surprised how often they are not applied. And that's a good question. It's not, people should be applying different tests, I think. It's often not as easy to detect problems as you would think. I think Scott in his talk, I'm not sure, but I think he has an example where if you just applied a test based on age, which is a protected feature, you would not see problems. But if you look at explanations, you actually see the model using another feature as a surrogate for age. And once you see the explanation, it becomes clear, but just doing a test based on age, you cannot detect it. But those are orthogonal techniques. We're not saying that explanations are a solution to fairness, just that they're a useful tool in addition to whatever else people should be using. So someone asked if the presentation deck is going to be shared. I can share my deck as soon as I finish. So someone was talking about another comment on fairness tests. Thanks, Alina. Someone else asked if the slides will be available. Yes. Love the idea of using Turkish to improve models. Thanks. This was a very rudimentary way of improving models. We're basically just removing words. I'd be interested in, like, it would be interesting to come up with better ideas. Or even if you just use Turkish to label more data, figuring out what data you should be looking at is something that I think explanations can be really helpful in. Someone asked if SHAP and LIME are useful for unsupervised models. They can be useful, but you have to define some metric of interest. So let's say you're doing clustering. SHAP and LIME can help you figure out questions such as, why are these two clustered together? Or why is this instance in this particular cluster? You have to define a target of explanation. If you don't have a target, then I don't think they're useful. But if you do have a target, then they can be useful. Is the focus on augmenting humans focus on understanding feature or overall decision? I'm not sure if I understand the question 100%, but augmenting humans, the focus, I guess, is on helping humans make better decisions. And that could be through understanding the data better, through understanding the features better, through understanding the overall process better. So if you think about making a diagnosis, there's a lot of features that humans already consider. A model could be useful by highlighting something that humans are not considering. So maybe a model says, hey, this is what I'm using to predict this particular symptom. And a human can go and say, okay, why is that? Maybe I should go and investigate whether that's a good feature or not. So that's a way in which it could be useful for the overall decision. Whereas if you're looking at an individual prediction, so let's say a judge making a bail decision, maybe the model can be helpful in just making the judge faster, which I'm not sure it's a good thing. I actually don't think it's a good thing. I think judges should be taking their time. But if you think just from an efficiency point of view, if a model can be used to, like, instead of having the judge carefully peruse each person and try to understand, the model could just highlight, hey, this person has, I don't know, 5 rearrests. Is this enough for you to make a bail decision? Or do you even need to look at the rest? Now, I'm not saying this is a good idea. I'm just saying, if you think of less high stakes decisions, that could be a way that it could be helpful. Sarah asked, which of these methods are applicable to deep learning where you don't have specific features? Well, Sarah, I think all of them, because even if deep learning, if you're not using specific features, like if you think of images or text, you can still come up with interpret representations that are not being used by the model, but that you can perturb. So for example, if you have an image, you can still hide parts of the image. Even if the method is not using those superpixels as features, you can still get useful explanations. So I think Scott will have a bunch of examples, if I'm not mistaken, of deep learning models. And I have a bunch of examples too, where we're explaining those models. Obviously, the glass box methods are not going to be applicable there, although there are hybrid techniques where you have a model that is a deep learning model that at some point produces a set of features that are then used by a glass box model. So there are some hybrids. Are there any use cases for model explanation for matrix factorization models? That's it's a bit tricky because matrix factorization, typically it's not easy to perturb an example and get different predictions since the training happens at the same time as you're producing decisions. So it's trickier. I don't know if there's any interpretable methods by design, but it is hard to run these black box methods because they all rely on perturbing examples, and it's hard if you have to retrain the model after every, if you have to like rerun matrix factorization every time. Someone asked, you didn't mention Lime's local interpretability, which gives superpixels on deep learning models. I did mention it. My example of the wolf, husky, and so on was based, sorry, both the wolf, husky, and the dog playing guitar were superpixels. Anchor also uses superpixels. I just didn't, I'm not going into the details as much because I'm focusing more here in this talk on the cheat sheet, I guess. I think that's all the questions we have. So unless there's any more questions, I will hand it over to Scott. And I'll share my slides on the chat. Thanks all. You're up, Scott.
All right, thanks. Let me take the screen from you. Can you guys see the slides?
Yes.
Great. Okay, so I'm going to dive in this section to focus on a particular area of explainable machine learning, which is the area that has been explored with game theory, and it focuses largely on what people consider feature attribution. So that's often can be either a global or a local explanation. We're talking about the framework that Marco just laid out. But I'm going to start by talking about the local explanations, because once you've understood local feature attribution, most, if not all, global feature attribution methods can effectively be derived as an aggregate measure of local importance values. So I'm going to start here with a very simple example that you may have seen before, but this will serve as an anchor point to reference all of the different applications that you can use for local feature explanations and how they actually connect back to human intuition. So imagine you're a data scientist, you're building a model, pick your favorite tool, and then that goes into something that you haven't really, the implementation doesn't matter. Really, the behavior is what we're interested in, right? So black box model explanations are all about understanding the behavior of a system where you treat the system as a black box. So in this case, if it's for a bank, you're going to get customer information. You might go into the model, spit out predictions about that customer, such as, will they have repayment problems? And then oftentimes there are real business decisions made on these things. And of course, this raises a lot of questions. Like Marco discussed earlier, there's a lot of humans that are involved in this process, and these humans often have a lot of questions because they're impacted by the model. So here is the data scientist who built it, and probably the first question that you should ask if you're the data scientist is how you should debug this thing. It's important to understand failure modes. It's important to understand, what are the unexpected things that has happened, because you've really extracted a lot of structure based on both model training biases and prior inductive biases and signal from a data set, and you produced a function. But you didn't define all of the ways that that function behaves. And so it's very important for you to kind of debug it and see if everything went the way you expected, or if there's stuff you need to fix. The customer, of course, is also interested. They're less interested in potentially debugging the model. They're more interested in understanding why they were denied, because this is an impactful decision for their life. And there's important reasons they need to know why that happened, if they need to change something, or maybe even in this case, the model might need to change something. And of course, there are many other stakeholders here as well, not the least of which are managers in a bank who are very curious, not just curious, but legally liable and to understand the financial risk of models when they put them into deployment, right? And of course, fairness and a bunch of other questions come up. And all of these depend on some level of transparency. So I think it's useful, given this scenario, to imagine what an explanation even looks like. There are many ways to produce an explanation, but one, maybe most common way is to think about, what if John knew, what if we didn't know anything about John, right? If we knew nothing about John, what we would predict is the base rate in our training data set, right? So if we're a bank and we on average see about a 16% default rate, then our model, we'll call that F, applied to our whole data set X. If we take the expected value of that, we're going to get something essentially, equal to the base rate. This is what we'd predict if we knew nothing about John. However, that's not what the model output, right? The output of the model was 22%. So what's the reason for this difference, this discrepancy between 16 and 22%? Well, how did we get from when we knew nothing about John to when we know everything about John? Well, that's the impact, the informational impact of observing these features. And that's what we want to explain. Right? We want to explain what's so special about John. That's what we really mean when we want a local explanation. So how can we go about doing this? Well, we can start at that base rate. And then what we can do is we can actually run the equivalent of an experiment, right? Just like you might run a randomized clinical trial or something like that to understand how the human body works and whether a certain input to that changes the output you're interested in. So also you can do the same thing for models, only it's much, much easier to experiment on models. In this case, what we'll do is we'll intervene and we'll spill out John's application for him, right? We'll set one of the features, in this case, the fact that his income was not verified, because these are all numbers from a real model. And when we do that, it bumps from 16 to 18%. So what that means is that when we learned that he did not have his income verified, in other words, the bank hasn't verified the amount of income that he reported, that increases the risk, not surprisingly, a few percent. Now, if we do this again and we fill out the next feature, his debt to income ratio is 30. It's pretty high, so that bumps his risk up to 21%. Now we fill out another feature. We're getting more and more information about John. And now we learn that he was delinquent on a payment 10 months ago, which again increases his risk. So the conditional expectation here is increasing as we learn more. Then we learn something good about John, good from the perspective of financial risk at least, is that he has no recent account openings. Right? So he hasn't gone out and got a bunch of credit recently. So that lowers his risk quite a bit. But then we see that he has 46 years of credit history, which interestingly, the model decided to use to raise his risk. And now in this simple case where there's only 5 features, we have the final output of the model at 22%. Now, what we've done is we've introduced a feature one at a time, and we sort of measured the change in the model's output as we did that, and that produced a number that we could assign, these phi values essentially, that tell us which features pushed the model higher, the model's output higher, and which pushed it lower, and by how much. Of course, there's a problem here, and that is that the order matters, right? You can't just do this in an arbitrary order and expect the same thing to happen every time. Now, if there was a linear model, of course, it wouldn't matter what order you did this in because the linear model is additive, right? So any sort of additive model that's separable between all of its features, you can do just any order you like and you're going to get the same impact. But for any model that has interaction effects, right, where 2 different features are, the model depends on an AND function or an OR function of features, that's going to, how the credit gets assigned will change depending on the order. Because if you introduce 2 features in an AND function, you won't see any of the effect till you introduce the second feature. So the second feature will get all the credit. And the opposite is true for the OR. So to see how that happens in a real example here, let's take a look at no recent account openings and 46 years of credit history. Okay, turns out that there's a strong interaction effect between these features. So the no recent account openings and 46 years of credit history, we can swap the order that we introduced them, and we can first fill out his credit history length and then fill out the fact that he didn't have any account openings. And when we do that, we realize that what's really happening is these things are kind of canceling each other out. Okay, so once we know that he has 46 years of credit history, the fact that he had no recent account openings is not helpful at all, right? So it actually doesn't improve his chances to have no recent account openings if he's had a really, really long credit history. But otherwise it does. And this type of interaction effect kind of begs the question, okay, maybe there's lots and lots of ways to assign credit, and we haven't really identified a good way to explain the model yet. Well, given this sort of uncertainty of choice here, I think it's useful to back up and ask if there are questions that have been asked like this before. And back in the game theory literature, back in the 1950s, there was a man named Lloyd Shapley who worked on cooperative games, and they came across problems very, very similar to this. So the problem that they were studying was if you have a group of players who come together and they form a team and they produce some, they produce something of value at the output that we'll measure with, let's say money as a kind of a surrogate measure of whatever they're producing. How should they split up that value among each of the players? Where we assume that the players contribute potentially very unequally and in ways that are very complex, right? There's some sort of very complementary roles between people, and all sorts of arbitrary combinations of people could be more or less productive. How can we essentially share credit evenly? How can we divide up the money in a fair way? Well, he went about this by writing down a series of axioms that became very foundational to game theory and defined things called the Shapley values. So he did very well in game theory, won a Nobel Prize back in 2012. And these Shapley values are one of the things he's best known for. And they're defined using a simple set of axioms, which is what makes them attractive. So essentially, he said, well, if you want to give all the money away and not give any extra or leave any left over, in other words, you allocate all the credit, then you are essentially saying, I want efficiency to hold, which in our case means we want a set of fee values that sum up to exactly the difference between the base rate and the model output. So the expected FX and the FX in our case. The second axiom is, okay, so let's assume that you want that. Let's also assume that if you have two features that the model treats identically, they should get the same credit. In other words, those two features always have the exact same impact on the model. I should treat them the same. So that's very similar to another axiomatization that you could choose, which is basically feature names don't matter. That's what that says. The third one is a dummy axiom, which basically says if a feature is not used by the model, then you should give it no credit, which makes sense. And the final one can either be stated as linearity, meaning that if you take two models or two functions or games and combine them linearly, so also the credit should combine linearly. And there's, I would say, a stronger argument, but harder to define, so I won't go into the details, called monotonicity, which essentially says that if you take a game and make a feature more important for that second game, then you shouldn't assign less credit to it according to your credit allocation. So these are alternative. You can either choose linearity or monotonicity, or anonymity or symmetry. So you choose 4 axioms, and suddenly you have a unique definition of how you should assign credit based on a set of axiomatic principles. That doesn't mean you don't want to relax these. Potentially you could imagine relaxing symmetry to give yourself some sort of prior where the feature names do matter. That can be useful in some situations. But it's very nice because this gives you a single right answer based on a set of assumptions. And so you know what assumptions you want to make. And if they look reasonable to you, then you know what answer you want to get at. So what does that look like though? What are these values? Let's see. Get them to go forward. So they're easy to define. The Shapley values result from the average of this ordering over all n factorial possible ordering. So essentially we computed these phi values. So phi 1 is for feature 1, phi 2 is for feature 2. We could redo the ordering so that phi 1 came later, maybe at the end or something, and we'd get a potentially different value for phi 1 if we had a nonlinear model. And if we did that for all n factorial orderings and took all the different phi 1 values we got and averaged them, that would be the final Shapley value for the first feature. So that's great, but terrible to compute if you want to do it exactly. All right, so this kind of leads to a conundrum where you have these really nice axioms showing you, oh, this seems like a really great way to go about this. But then once you actually try and compute it, it becomes intractable. Now, of course, you can approximate it with just random sampling. And that is certainly one approach that you could do in the package I maintain, Shap, or probably some others as well. But if you want to solve this exactly, it turns out to be quite hard. In fact, NP hard. So there's not going to be any straightforward general solution that we can come up with that will solve this for all models. However, you can make this surprisingly fast for very large classes of models. And that's a lot of the work that I've done, but would take the entire rest of the time to talk about. So I'm not going to dig into the implementation details. But if you were to use the SHAP package, for example, on gradient boosted decision trees or linear models or other kind of well-defined model classes, we can compute these exactly in very low order polynomial time, which makes it nice and much more practical in practice. But let's assume that we've solved that. We've made these practical and we want to apply them. What I want to do is take the next chunk of time that we have here and dig into a couple things. I want to describe some intuitions. So I described the very basic level intuition here, but I want to go a bit deeper there. Intuitions on what these values mean by applying them to simple models, and then motivations for the dangers, the interpretability dangers of actually using too simple of a model, like what can go wrong. if you have a model with too much bias, which is what a simple model has. And then I'm going to talk about a variety of applications. And in each application, I think there's an opportunity to hopefully kind of inspire you with ways you can use explainable AI in your own practice and work and research. And also, I hope there's going to be some useful warnings or highlighting some pitfalls that are easy to fall into. So let's start with intuitions and applications to linear models. So I'm going to start with linear models, and I'll just slowly increase the complexity of the model. So what happens when so you can say, oh, great, you've come up with this explanation method that you can apply to any model, and it tells me how the model is working. Probably one of the first things you should do to understand what's really going on is you should apply it to a very, very simple model that you think you already know what it does, and ask, what are you going to tell me in that case? Right, and that's what we'll do here. So let's take a simple scikit-learn linear regression, not even logistic regression, just a simple mean squared error linear regression. When we do that, we can plot the partial dependence plot, which, if you're not familiar, is essentially just the average of that model's output when we change the a certain feature and move its value around. So that's the blue line here. That's the partial dependence plot. So we see kind of the impact of this feature. So the feature value is on the x-axis, and the impact on the model's output is on the y-axis. And as we move that feature's value back and forth, we can see the change in the model's output. And of course, it's a linear model, so it's just a coefficient times this feature value. We're going to get a line. But what are the Shapley values here? What are the Shapley values of these conditional expectations? Well, if we, in order to define the conditional expectation, you of course need some kind of background distribution, some distribution that represents missing or not present. Often that's a training data set, but you can set that to a lot of interesting alternatives to get insight into lots of things that could be going on. So sometimes you may want to compare your difference to if you're in loans, maybe you want to compare how this feature is important as compared to the typical person in the accepted group, or the typical person in the rejected group, or the typical person at the boundary. These are all useful parameterizations. But in this case, to maintain a very close connection with the partial dependence plot, we're just going to use the training data set. So the histogram shown on the bottom is the histogram of training samples, and I think this is income, annual income for someone. And you can see that the model output goes up as the income goes up. And what we can do is we can actually take the average impact on the model, right? So this impact on the model output here is really actually the model's output. So 0.5, 0.6, 0.7, that's the model's output on average when this feature is varied. And the gray line here is the actual average impact of this feature, right? So this is the average impact of the feature. It's the centered value here. And what we're essentially doing with the Shap value is, if you look at the right hand side, there's a dashed line. You can see a vertical red line going up, and that's a positive Shap value. And what it says is that all these, you can go through all the game theory and all the axioms and all the conditional expectations, but at the end of the day, when you apply it to a linear model, it's very simple. It's simply beta times x minus the mean value of x, right? That there tells you the Shap value for a linear model. It's easy to compute, it's very closed form, and the intuition is, I think, helpful. So if you look at the right-hand side, why is this value positive and why is it large? Well, it gets larger the steeper the slope. So of course, if your beta gets bigger, you're going to get a larger and larger Shap value, which makes sense, has a bigger and bigger impact. But it also has a lot to do with being atypical, right? Because we're subtracting or mean centering our features value. So if I get a value that is very close to the center of this distribution, I'm going to get a low Shap value because the informational value is low, right? There's no surprise that you have an average income, so it doesn't really change my prediction from the kind of base value that I would start with if I didn't know anything. But once you get to extreme values, extreme in the case that compared to whatever distribution you're considering, so back in the 1990s, apparently an income of 140,000 looks like the 98th, 99th percentile. So in that case, you get a very large Shap value because the line is going up and you are much above the mean. Conversely, if you are below normal, right, so you have a lower income than average, you would end up showing a negative Shap value. And so that's what you get with a lower line. And let's see, I'm just trying to get this to skip. There we go. So let's increase the complexity here just a little bit. Okay, so now we can see what these values, what these explanations produce when we have a linear model. What about an additive model? So this is a generalized additive model where just, kind of shoehorned XGBoost to do this. You should probably use the EBMs that Rich has later to do this if you want more accuracy. But you can just set the max depth equal to 1 in any GBM package, and you'll get an additive model, which means there's no interaction effects between the features, but we're no longer constrained to have straight lines. We can have nonlinear marginals. So the same partial dependence plot is being shown, and the SHAP values, again, are the height between the partial dependence plot and the average model output, okay? With the same sort of above and below the mean, giving you positive and negative values. So positive value means this feature increases more than average. Negative value means it decreases you more than average. So this very close connection essentially means that if I were to plot my entire data set of SHAP values for an additive model, I would literally just be tracing out the partial dependence plot of the feature. So this makes sense. Now what happens if we write this down in math? Well, remember, additive models can be written down as functions of individual features that are then added together. So what we do is we simply take the function evaluated at the current feature value that we're explaining, and we subtract the mean over all feature values of that individual features function. So this is, again, just a simple closed form analytic solution for what these values mean when you apply them to a simple GAM model. And it's reassuring to find that these are the types of values you would compute even if you had never thought about game theory in the first place. You get the same kind of intuitive results. Now, what happens, however, when you ask to explain a more complex model, one with interaction effects? Well, this is where the exact relationship between a partial dependence plot and these attribution values begins to break down. And how nonlinear your model is will determine how much this breaks down. Why does nonlinearity affect things? Well, again, if we look at the dashed line on the right-hand side, we'll see that the SHAP value now doesn't measure the height between the mean and the blue line. Instead, it's significantly higher. And the reason is because different people have different, may all have the same income, but have other factors that are different. So let's say, for example, that you were a day trader and you made $140,000 last year. That could mean a lot. That could mean something very, very different than if you were a doctor and made $140,000 last year. Because the doctor is very likely to continue to make $140,000 the following year, whereas a day trader might have very, much lower likelihood of maintaining a steady income. And these types of interaction effects, of course, when picked up by the model, mean that having an income of $140,000, if you have a feature value of employment doctor, may be much more important than if your employment is a day trader. Okay, so this produces vertical dispersion. And with those interaction intuitions behind, I'm going to kind of step forward and talk about how to use this. So again, just as a summary, this is an example of the type of explanation that we get. So if you're just to compute a local explanation and do a SHAP.plots.waterfall at the end of the day, you would get this. This is a standard census income data set where you're predicting chance of making over 50K based on a variety of demographic features. And you can see we start at the expected value, which is, these are log odds, so 2.6 negative log odds, pretty unlikely that you're gonna make over 50K. Some things tend to increase, some things tend to decrease. The big thing affecting with this person, of course, is their capital gain. But the issue here is that if you add all of these effects together, you get exactly the output of the model for this person, which is negative 5.8. This is from a GBM model. Okay, so now that we have that kind of intuition under our belt, let's talk about how you can represent global model structure with these local feature importance values. And I'm going to talk about it from a tabular data structure viewpoint, but again, you can do something similar in many ways for text and images. So for simple tabular data, you have rows, which represent samples, and then you have a set of features. And when you plug that into a model, of course, you get an output. And we're going to assume that output is a single number, but of course, you can run it for multi-output models, and you're just going to get multiple explanations for each output, one explanation for each output. And then if we use an explainer, like tree explainer in this case, if you're using like a GBM, then you're going to get an explanation matrix, these attributions, chat values that are exactly the same shape as the input. So you have two parallel matrices. You have your data matrix and you have your explanation matrix, your feature attribution matrix. And it's helpful to think about what the units are here, right? So the units of your gray matrix on the left are going to be different for each column because each column is a different feature, could potentially have very different units. Age could be in years, blood pressure could be in, milligrams of mercury, income is going to be in dollars. These are very, very different units. But the units of the blue matrix are all the same because they are all in the units of the model's output because they all represent differences in model output changes. So if your model's output is risk of death or likelihood of making a lot of money, then they're all going to be in the same inputs. And so they're easily comparable. And some of that shows up later in these downstream applications, okay? But you could say like, okay, why do I even need these matrices? I could just train a linear model. And if I really, really want transparency, maybe that's what I should do. Okay? But to motivate why we should kind of step back and think a little bit more model agnostically, I want to talk about some of the trade-offs that you need to keep in mind when you are dealing with very, very simple linear models. So the interpretability cost of model bias is the source of the issue here. So to talk about this, let's imagine we have a data set. It's a medical data set. It's got about 12 features in it. And it's just standard measurements you might get at a doctor's office taken from a data set here in the US, I think a few decades ago. And in this data set, we took two of the features, body mass index, so BMI, and age, and we created a simulated risk outcome from it. Okay, so the data itself is real, but the outcome was simulated so that we could control the actual data generating distribution of the label. And we started by creating a linear relationship between BMI and age that produced sort of a, ultimately a binary feature that was, had this thing or not, where the risk sort of goes according to this gradient. But then what we did is we changed the relationship so that it was more and more nonlinear. Okay, so we've shown 5 different points or 6 different points along this line, from fully linear all the way to, a reasonably strong quadratic relationship. And now what we have is lots and lots and lots of data sets that have labels generated from a more or less linearity in the true data generating distributions. The amount of nonlinearity increases as we go to the right. So, we're talking to machine learning folks here. No one's going to be surprised that there's this bias variance trade-off, right? So if you have the true model, so the true model, purple line at the bottom, so that's the best you could do. And on the far left, you'll see when we have a perfectly linear true data set, the relationship with our label is actually linear, then no surprise, logistic regression almost perfectly matches the true model and gives us the best answer. In contrast, when you run a gradient boosted model on top of this, we do not get quite as much, we don't quite get to the right answer, but we get close. And the cost that we pay there is, of course, the variance. The increased flexibility of the boosting model pays a price. And that price in accuracy is shown here as this fixed offset. However, if we begin to add nonlinearity into the model, we can see that quickly begins to hurt the linear model, but it doesn't affect the gradient boosted decision tree. All right, so this is exactly the trade-off between model bias versus model variance. The variance is a fixed cost as the shape of the model changes. However, the bias grows significantly. And you can see by the time we get to the far right, there's a significant amount of accuracy that's been lost due to the incorrect bias of the linear model. The bias of the linear model says, I believe the relationship is linear, but of course it's not truly linear. What's, I think, less appreciated and what I want to highlight here is that in addition to there being an accuracy that gets lost when you have a bad model bias, a bias that doesn't match the true data set relationship, there's also an explainability that gets lost often due to this bias. So what do I mean by this? Well, obviously a linear model itself is easy to look at and understand what it is doing, right? The functional form is not hard to see, but why it is taking that functional form can be very complex. And to see that, let's start by showing what % of weight gets assigned to the 2 features we know really matter, BMI and age, versus other features in the data set. There are like 10 other features in this data set that we know don't matter. However, they are, this is a real data set. So there are real correlations and nonlinear dependencies between BMI, age, and these other features. And so as we begin to add a little bit of nonlinearity into the function, the linear model can't fit it, but it can try and rely on other features that have slight nonlinear correlations with the real features in order to create a little bit of curve or bend in the linear model's fit. And so how much does that gain you in accuracy? Well, we can look at the top plot and see the difference between the dashed red line and the solid red line. The dashed red line is where you force the linear model to only use the 2 correct features, whereas the solid red line is when you allow it to depend on any of the features. And you can see that it actually did gain a very slight bit of accuracy by some sort of cancellation effects. But these cancellation effects prove to be a huge part of the model. So by the time you get all the way over to a reasonably quadratic function on the far right, you have over 20% of the model's coefficients assigned to irrelevant features, which means there's a strong amount of cancellation effect going on. In fact, I don't have the plot here, but if you look at the sum of the absolute values of the beta coefficients, it gets bigger and bigger and bigger, which of course is implying that, of course, the model output isn't getting bigger and bigger and bigger as the quadratics happen. Instead, what's happening is that we're getting more and more cancellation effects. And so even though you have a very simple model, that simple model is actually much harder to explain than the gradient boosted decision tree, because the decision tree didn't have this bias, it just had variance, and the variance left it free to choose the true 2 features, even if those 2 features had some nonlinear relationship to the output label. But once the linear model had a mismatch, it began depending in very complex ways on the output, and suddenly you may see that it depends on blood pressure and height and all these other features, but in reality it's just doing very strong cancellation effects, and you probably have actually no idea why it depended on them unless you understand the subtle intricate dependency structures in the data and how those cancellation effects occur. Okay, so that's one kind of motivational piece that I think you should keep in mind whenever you're dealing with an explainable AI. A simpler model is not always better. If your simple model begins to severely disagree with the statistics and structure of your data set, you are not necessarily going to get a more interpretable model by choosing a simpler model. You may get one that is doing crazy things to try and fit something that is not designed to fit. Now, that being said, this is a logistic regression model, so this is a linear model. And this plot here, I'll kind of do a little look ahead, is as I would say, very compelling evidence for always using something like a Rich's EBMs instead of a linear model, because there's very little interpretability cost lost to the EBMs, but they're going to be much, much less susceptible to this type of cancellation problems than you would find in a linear system. Okay, so I'm going to move from one danger to another, I guess. This is one about global measures of feature importance. So the first one was about, well, shouldn't I just use a simple model? Well, maybe, but you should be very careful about the downsides of that. The second one is here about global feature importance. If you think about it, this is probably the most popular way to explain a model, and has been maybe in statistics or data science since the beginning. And it's spurred, of course, by the fact that linear models come with a really nice summary of their behavior, these beta coefficients. You can just sort of plot them. But almost any model, you just plot a bar chart that says, what are the features that matter the most? Almost every model will do that, a random forest, linear models, even people have done this with SVMs and all sorts of things, and linear neural nets. So when I produce this, though, I think it's really important to kind of keep in mind, what do we learn? Okay, so here I'm going to use as an example a mortality risk model. So this model was trained on about 15,000 people in the 1970s. They were surveyed randomly in the United States as part of a big government survey program, and then they were followed for 20 years for mortality and a bunch of other things. So we get to predict all-cause mortality from the general US population in the 1970s using a very, very large data sample. So this is really a quite nice mortality model data set. And we can list off what are the #1 features that impact your risk of mortality in the next 20 years based on what was recorded in these sort of standard procedures. Which, if you think about it for a sec, I'll let you think, like, what do you think the most important feature is? Turns out it's age. Okay, so no big surprise there, I guess, but the #1 predictor of your risk of mortality is being old. And it turns out that the #2, as learned by, I should clarify, this is a nonlinear XGBoost model trained with a Cox proportional hazards model. So it's a fairly complex but well-fit model. The next feature turns out to be being male as the #1 killer after being old. And then after that, you might find the kind of things that most people would guess in the first place, like systolic blood pressure or white blood cells or body mass index, things that doctors will tell you to intervene on to help your health. And of course, it turns out that there's a long tail of these things, right? They measured all kinds of things about these patients. And if you look at this global feature importance chart, you could come away with the conclusion that age and sex matter a lot. And maybe systolic blood pressure and white blood cells, which is kind of a stand-in for inflammation and weight, you kind of get a feel for what are the top issues that matter. But what's really important to keep in mind here is that you're conflating the prevalence of an effect with the magnitude of an effect when you do this, right? So in order for us to have a global feature importance that is large, you need to both be prevalent, meaning that this affects many people in the data set that we're averaging over, and also a reasonably large magnitude. So something that is very prevalent but has a low magnitude will of course get a low global and feature importance. And perhaps even more interestingly, something with a high magnitude but low prevalence will also achieve a very low global feature importance. So that means if we're doing this, we need to think about how could we reveal high magnitude mortality effects? Because standard global and feature importance methods do not do that. Well, this is where local explanations, I think, have a important role to play. So rather than explaining things globally like this, let's imagine we have explained local explanations for every sample in the data set that we use to create this global feature importance. So on the x-axis, instead of having some global measure, we're now going to have a local measure, which is the SHAP value, the impact in the model's output, which is their log relative risk of mortality. And to plot this, we're going to use a dot for every person. There's like 14,000 people. We're going to put a dot for every person, and then we'll color those dots according to the value of the feature, just so we can visualize this. And when we do this using a B-swarm plot, which means the dots pile up to show density, you can see almost everyone for blood protein, the one at the very bottom of the list here, almost everyone is 0. Okay, it means they don't have protein floating around in their blood, significant amounts of it, which is good. Means your kidneys are working and a few other things. But what you do see is that there's a long tail, right? What is this? Rare high magnitude effects. So while blood protein looks like maybe the least important feature in all of the ones I'm showing here, that is potentially maybe true at like a population health perspective, but it's certainly not true for that red dot on the far tail there, right? There's that dot of that person who's got, I'd say 0.6, 0.7 impact. I mean, that's about 10, 15 years off their life, I would say, if I remember right, in terms of this scale. It's essentially linear with years on this scale. And that's a huge, huge impact on this person's life expectancy. And it's entirely driven by this feature that is very, very low on the scale of global feature importance. So I think this highlights the fact that when you do global feature importance, you're essentially washing away rare high magnitude effects, which is often stuff you're very, very interested in, be that for fairness, be that for mortality, be that for all sorts of different things. We care about small subgroups and what's happening to them. And if you have local explanations of your whole data set, you can begin to see these outliers and these subgroups and not just wash them away in global summary statistics. So of course, if we do that for the whole thing, we'll see that there's a very depressing picture, if you will, because there's lots of long tails stretching out to the right, okay? Which means there's lots of ways to die young, right? I mean, if you're wildly out of range in your blood pressure, you're wildly out of range in your blood protein, or you're wildly overinflamed or super, super underweight, all of these things have huge impacts on your mortality risk. Unfortunately, if you look the other way, you'll note that there are not any sort of catastrophically large ways to deviate out of normal and then live way longer, right? So no one has like a super weird blood albumin level that will make them live another 20 years. Right? So there's lots of ways to break, not a lot of ways to magically fix everything, which isn't surprising, but it's something that you would never have understood. These types of patterns just aren't the things you're going to see if you just drop everything down into a single global feature importance. So I guess that's another both reason to use these local methods, and also a warning if you're just using something that collapses your data into a single ranked list. But to dig a little deeper, I'm going to stop. Okay, so we just talked about global feature importance and why these local explanations can be a potentially significant improvement over them. Now I want to talk about how we can potentially improve over basics plots like partial dependence plots. So here's an example where we have a partial dependence plot style layout where we have the feature, in this case, systolic blood pressure, on the x-axis, and we have the SHAP value for the systolic blood pressure on the y-axis. And again, this is log relative risk of mortality. And when we plot a dot for every person, just like we did before, we can see that the risk is lowest at about 120, which makes sense, and then just increases more or less linearly, which means exponentially in your risk of mortality from there. Okay, so 120 all the way up to 220, you see this sort of not surprising systolic blood pressure risk. However, we would have gotten the same thing from a partial dependence plot, but what we would have missed is this vertical dispersion, right? So these are all people that have a blood pressure of 180, systolic blood pressure, but that impacted the model's prediction of their mortality risk very differently depending on who they were. For some people, it increased their risk by maybe a few years, and others it increased the risk, decreased their life expectancy by almost decades. Why is that? What is the difference here? Well, these are driven by interaction effects, like we talked about before. Right? Vertical dispersion means that systolic blood pressure has an impact on the model, but it depends on other features. What other features does it depend on? Well, it turns out that you can use color to kind of understand what could cause this separation. In this case, if we color by age, we'll see that the blue dots are young, the red dots are older, and what we've identified is this danger of early onset high blood pressure, right? So these blue dots essentially say if you're 30 years old or 40 years old and you have a blood pressure of 180, that is going to have a huge impact on your life expectancy. Whereas if you're 70 plus and you get this, it's still going to have a significant impact on your life expectancy, but it's not going to be to the same extent. Perhaps because you have other competing problems that you have to deal with, but also it could just represent a less severe disease form. But these are the types of interaction effects that I think are much better to see with these types of scatter plots and would easily be lost in a kind of partial dependence view of the world. Remember, if there's no interaction effects, these plots degrade to exactly the partial dependence plot. So if you get a line coming out of this, which is a partial dependence plot, then what you've essentially shown is that a partial dependence plot tells you everything you need to know. But once you start seeing vertical dispersion, I think it's important to know where that vertical dispersion is, right? Interaction effects are very prevalent with blood pressures over 150. They're less impactful around 120 to 140. So like, where does this interaction effect matter most, et cetera, is important things to keep in mind. Okay, so I also want to go into what's maybe even a more subtle use of these interaction effects. Okay, so here's another plot. This is the plot between age and the mortality risk. And you can see a very linear increase. And since this is the log scale, this is an exponential increase in mortality risk as you age, okay? Which kind of makes sense. That's kind of how the world works. And then what you can see here is that blue dots on the top and red dots on the bottom show that men have a higher mortality risk than women within a certain age range, right? You don't see that separation in the 30s and 40s, but once you get into close to 50, 60, then you see this very clear separation between men and women. Well, it turns out that you can actually extend these game theoretic concepts to interaction effects. And when you do that, you get the ability to plot these interaction effects by themselves. So here we're plotting the interaction effect between age and sex over someone's lifetime, okay? So we have age, one of the features on the x-axis, we color by the second feature, and then we use the y-axis for the interaction effect. And what we can see is that the difference between the risk of men and women, while always larger, so women always have a lower risk than men throughout their entire life, that risk difference is the largest at the age 60. And this very clear picture, this clear peak is something that you would very easily miss if you weren't sort of digging into these effects directly using these local scatter plot explanations. Okay, I'm going to go fairly quickly over this because I want to spend a little bit more time on what we have after this. But I want to touch briefly on the notion of the ability to use these local explanations. So we talked about how we can use them to improve our global summary plots, right? By giving us richer summaries that don't hide rare high magnitude effects. We talked about how we could improve partial dependence plots by showing when interaction effects are important and when they're not through vertical dispersion. We talked about how we can actually pull those interaction effects out themselves and use them to gain insights into the data. And what I want to talk about next is how you can use local explanations to cluster your data. So imagine that you're interested, these are again the 14,000 people from this mortality data set that we've been using. Imagine you want to cluster these people in order to better understand how to sell them shoes. Well, I probably wouldn't want to be clustering them by their blood pressure or their cholesterol level. These are things that maybe age, that might be relevant for shoe choice, but clearly there's why I'm doing the clustering will totally change what a good clustering is, right? A good clustering for the marketer trying to sell shoes could be very different than the clustering that I want to show the doctor or the population health person about how to improve life expectancy. In this case, we've trained a model to predict life expectancy. So we can bias our clustering to be a good separation of people with respect to life expectancy by clustering not the original features, okay, which could be used for lots of different prediction tasks, but instead by clustering the explanations. So what we're doing is we're clustering people who have the similar risk for the similar reason. And that's something we'll call supervised clustering, where essentially we can easily compare, because remember, we're all in the same units. These all have the same units, which are the output of the model. So I don't have to compare, years to categorical variables to whatever the white blood cell measurement that the lab used units were. All of those are very, very hard to calibrate and compare to each other. It's one of the main challenges in clustering is computing these calibrations. But once you've trained a supervised model, if you can produce these local explanations for it, you essentially already have a calibration. You can put them all into the same units, which is their impact on the model's output, and you can use that for clustering, and we get lots of interesting subtypes. So this is meant to kind of spur ideas in the use of explainable AI tools for downstream tasks. Another way I want to kind of spur ideas is talking about not just explaining the model's output, okay, like the risk went up or down, but other output, other aspects of the model's behavior. So for example, the model's loss. So here we're talking about how can we explain the model's loss and what would that do and how would that be helpful? Well, imagine you want to do model monitoring, right? So you've deployed a model and you want to see how's that model performing over time. Well, one of the most, straightforward ways to do that would just be to plot its loss over time. So this is an example from a hospital where we have, I would say, 4 or 5 years of data, and we trained a model to predict how long procedures take. This is important for doctor scheduling and things like this, how long procedures take in the hospital. We trained using the first year, and then we predicted and just let it run on this historical data. So it's supposed to be very, very clean data because all the bugs have been observed and then fixed and then put back together. Like, there's a lot of man hours that went into making this good historical clean data, okay? So you expect to find many fewer bugs than you would in live deployment, but still we can use it as a surrogate for what we might be able to observe over time if we deployed a model and then just let it run and see how it may degrade over time or how bugs may creep in. So what you can see is the mean squared error smooth a little bit so that it doesn't, I think of the nearest 1,000 cases. So this is like hundreds of thousands of procedures that we're looking at here. And you don't really see anything but random fluctuations typically, okay? And I can say that because we actually introduced a bug here, right? So we said, well, if we're interested in finding bugs in the data, let's actually put a bug in and see if we can see it. And the answer is, well, it's very hard to see it. So again, this is the test performance. Somewhere in this test window, we introduced a bug that clearly broke some of the features and hurt model performance. But you can't tell, right? Because there are thousands of features that go into this model, and we only broke 2 of them. And it's just super hard to tell because it's swamped with all the other features. We can't understand the impact of each feature on that model's loss. So what we can do is we can apply SHAP or another type of explanation method to explain the loss of the model And when we do that, we'll essentially deconvolve the loss among each of the features. So now we have a vector, which is the length of my features. And when I sum up that vector, I get my model's mean squared error. But it tells me which feature caused the error to go up or down. So here's an example of what happens when we plot that for one of the features where we actually broke it using the bug. So this is a label of, are you in room number 6 in the hospital? And what we did is we actually just swapped the labels of room 6 and 20 in the hospital, which, you know, is a fairly easy bug you could imagine happening during some procedure of some sort, you know, data IT procedure, that is. And what happens is you can see, so the red dots are when this value is 1 and the blue is when it's 0. So 1 means you're in this room. You can see that the blue dots basically give you no information. They have no effect on the model's loss, as expected, because not knowing you're in that room doesn't really tell me much, because you could be in, you know, hundreds of other rooms. However, when we do know you're in this room, it lowers the loss. It's informative, which is good. So the red dots are actually negative. They're a negative value, meaning they lower the loss until about the end of 2014. And then you can see suddenly they're predominantly positive, meaning they're increasing the model's loss. So the question is, you know, now can you find where we introduced the bug? And of course, the answer is yes. It's much, much easier now to identify when a problem happened in your data by looking at the bottom plot than the top plot. And that's because we've deconvolved the signal. It's a much, much stronger signal now. And it's important to note here, this is not dependent on monitoring your marginal statistics of your input features. So that means there is no reason, like the rooms here can have equal occupancy frequencies. So that if I was to look at the distribution of rooms, of these two rooms, and after the bug, they're gonna have the same histogram before and after. What's changed is their relationship to the label, the true thing we're trying to predict. And that's something that you're just not going to catch with most current model monitoring methods, but you will if you apply explainability to model monitoring. And of course, we found not just the synthetic stuff, but real stuff that didn't manage to get cleaned up in this data set. So like a EMR record where, you know, this is super helpful because now you know which feature is causing the problem too, right? This isn't just my model has broken at this point in time. It's this feature caused my model to break at this point in time, which is super helpful. So here we know that general anesthesia there was an IT problem that never got recorded, and actually weren't even aware of this till after the debug. Here's an example of feature drift, where some changes in procedures in the hospital made a feature that was, you know, very informative at the first year, changed significantly over the following years. Okay, to wrap things up here, I think the last thing, I have two things to cover, but I want to spend a moment here on explaining fairness metrics. So when people talk about explainability and transparency, often they're interested in controlling for negative harms of their model or things that could go wrong with it. And of course, one thing that can go wrong with models very easily is they can produce biased or unfair outcomes under a variety of metrics and definitions of that. So here's an example from the finance industry where we have a model that I trained on publicly available lending data as an XGBoost model, trained to predict the risk of default. Okay. So this is not from a real financial institution, but it's something that I just trained in a not an unreasonable way. I just used all the data and predicted the label. And what I got was this dependence plot between the month since first credit card was opened and the risk of defaulting. And it's kind of interesting what you see here, right? You can see that you have a very high risk on the left-hand side that drops off very quickly. So this means basically no credit history really increases your risk. But once you've had, you know, a couple of years of credit history, maybe 5 to 10, like you've got quite a bit of, you know, your risk is now dropped significantly. And it continues to go down, and there's a lot of interaction effects driving some dispersion. But then you see this interesting uptick here at the final tail. And I think this is what Marco mentioned earlier, is that like, you may not necessarily see this kind of dispersion very easily by global metrics, but it's super clear when you're looking at this type of feature dependent structure. And when you come as a human, you can bring your own kind of understanding of how the world works, and you can quickly realize things like, I think what we're doing is we're applying much higher risk for retirement age individuals, because months, 400 months is about 500 months. I mean, this is about 40, 45 years after your first credit card got opened. That's pretty close. If you add 45 years to 20, if you assume they got their first credit card around then, you're looking at 65 years old. So essentially, we're identifying retirement age individuals based on how long they've had a credit history, which, if you're at all familiar with the financial industry, is a big no-no, because age is a protected class. You can't discriminate credit based on someone's age, but that is exactly what this model is doing. And it's doing it apparently because older people applying for this type of credit tend to be in a higher risk category. That may be true, but it's not one of the factors that you're allowed to use. And this is a very clear discrimination case that you would not want to have show up legally or morally. So this is an example of how inspecting your model can be super helpful for fairness. I also want to talk about how quantifying fairness can benefit from transparency and interpretability. So here's an example where we actually created a simulated synthetic data set so that we knew exactly how the whole system worked. And we were essentially predicting some risk score between men and women, let's imagine default risk. And we measured the demographic parity difference between women and men. Okay, now what that means is you essentially just take the average over all the women, the average over all the men, you subtract the two groups, and you see if the if there's some sort of statistically different outcome between these groups. And if so, that may be an indication that you got to follow up and figure out why there's this disparity. It's super common. There's also several other metrics. But if you're thinking, oh, I would actually want to do equalized odds or something else, all of these methods, what I'm about to describe applies equally to any quantified metric like this, but I'm going to use demographic parity for clarity here. Well, now that we've seen this, we can see, wow, there's a strong difference in demographic parity. What caused this? Well, because we simulated the data, we know in this case that it's because we intentionally introduced an underreporting bias for women's income. Okay, just to see what would happen. And indeed, it did create a demographic parity difference when we trained a model on that data. Okay, so if for some reason you're just less accurate at getting women's income and you're biased, you're more likely to miss income sources for women than for men, then you're going to end up with this disparity. But that's really hard to get at just from this single number. Like if you just get this number, it's going to be very tricky to figure out what drove it, how do I debug this, what's the next thing to do? And that's where I think transparency can have a useful impact. So here's an example where we actually applied SHAP to explain this model. And we explained all of the samples, all the women, all the men. And then we took the explanations and of all the samples, and we split them into the two groups that we wanted to compare, in this case, women versus men. And then we did this same, remember, all the explanations are in the units of the model's output. So whatever you're doing to compute demographic parity difference, you can also do to the attributions applied to each feature separately. And we do that for job history, reported income, credit inquiries, and late payments, which are the 4 features that are involved in this scenario. And remember, I said what we really did was we created an underreporting bias for women's income. And there are non-linear effects here. There's all sorts of stuff going on in this simulated data to make it a bit more realistic, but we know what's happened. It's the reporting income is the problem. And when you do an explanation and actually explain this demographic parity difference, so again, the 4 bars on the bottom, if you sum them up, they equal the bar on the top. They tell you what feature is actually driving this difference. And that can be super helpful, both because the top bar could be 0 because they're canceled out by, if job history discriminates against men and reported income against women, then they could look great in the overall difference, but they would be bad in each subgroup. And I think this is kind of an important thing that I think it's useful for people to consider when they're thinking about transparency. You want transparency not only in your model's output, not only in your model's loss, but you also want transparency in the fairness metrics you're using to keep track of your models. Okay, I'm going to wrap things up here and not go too much into the structure because of the sake of time for questions and such. But I do want to point out that a lot of the work we're doing right now is accounting for the structure of the data that you have in the game. So I said this is all tied back to game theory and you can write axioms and things like that. Well, what if I know that there's a lot of structure in my data? How can that help me? Well, it turns out you can leverage that by encoding it as rules in your game, and then you can connect things back to game theory. And there are a lot of things in game theory that have been already studied for decades on how to encode structured games, and we can apply that to structured explanations. Essentially, this allows us to not just think about our input X to our model, but also to imagine all of the history and semantics that are going into those features as the structure of the data. So here's a few examples that are actually in the SHAP package today, where you can create a hierarchical clustering based on the predictive power redundancy of these features, and then use that during your explanations. You can even plot them in the bar chart. So here you'll see the the income prediction task again, and there's a two features, relationship and marital status. They're not identical. So if you did a clustering based on the original features, you wouldn't get this quite as well. But we train, all pairs XGBoost model on here and see that they're essentially perfectly redundant in their predictive power. So we can group them together and display them together in our explanations, and in fact, even perturb them together to achieve realism during our perturbation process. We can also, do this for global feature attribution. We can cut the tree to allow better visualizations. And we can do this on rich data like text, right? So let's imagine that I want to explain a series, a big chunk of text, and I want to do it in a model agnostic fashion. Here's a sentiment analysis task. But I don't want to just perturb words randomly, right? There's real important structure in this called a parse tree. Imagine a constituency parse of this structured sentence. How do I use that structure to realistically perturb this thing and also be much, much more efficient about how I can explain my model? And this is an example here where I think we've run this thing like 50 or 100 times. Like we've only executed the underlying transformer model like 50 or 100 times, and yet we're able to get very high resolution explanations on this has like 500 or more tokens in it. And you can see the explanation for this particular sentiment analysis. So a negative means the model believes that this is a poor review of the model. And the number one reason it thinks that is because of the name of the movie is Life Stinks. And so of course it latched in on, I found Life Stinks and I just forgot about everything else. And so it thought, well, it's I stinks, this must be a bad movie, when in reality, it's just described in the title of the movie. So yeah, structures can be super helpful, and we're in the middle of doing a lot of fun things here. That's all, and happy to take questions. Thanks.
There's a question or two in the chat, if you're able to see it, Scott.
Yeah, I am just.
And if you're not able to see it, I can read them for you.
Give me 5 seconds, and if I can't get it then, yeah, how about you read it? Because I cannot get out of my presentation and read them.
Question from DP. Would the statistical significance of the coefficients in the linear model not account for the loss in explainability? So this was much earlier in your presentation.
Sure, yeah.
If you've got many coefficients, would not, significance of all of them be reduced on the individual ones, I guess?
Well, I guess there's 2 points there. One is, would you be able to identify that something is wrong by looking at the fact that your coefficients have a large error bar on them? Maybe. It depends on the size of your data set. Because there are very real statistical associations that do exist between these features and that do allow a reasonable, a very small improvement in accuracy. So given enough data, the uncertainty for all those coefficients should actually go to 0. That being said, it is likely to be high, and this is likely to be more of an issue when you see very high coefficient values and high uncertainty associated with them. Now, that being said, even if you saw that, you still haven't gained interpretability. What you've gained is a very important thing, which is now you know not to trust your linear model or not to interpret it, but it hasn't gotten you as far as what you would have gotten if you'd run an EBM or XGBoost model and actually gotten something that had reasonable statistical significance, maybe through a bootstrap resample or something to understand that, and depended on the right features, right? I don't know if that answers, but I hope that's helpful.
Yeah, and there's a question from Max Huang. This was also made a little while ago, which is unfortunately too short for me now to remember the context. What if there is a confounding effect? But I'm sorry, I don't know what this was in reference to.
Sure.
So Max, I don't know if you're able to suddenly jump in and explain to us in more detail what your question was.
Let's see.
And of course, if anyone else has questions, feel free to type them into the chat window.
Okay, and I am now on here. What time point are you at for asking questions? I can see the talks now. Okay,
so the first question I asked you was from 12:20.
Okay.
And then the one from Max was 12:40, if that helps you, if you know where you were in your presentation at that time.
Sure, that makes sense. Yeah, Let's see. I guess I can talk in general about confounding because I think that's an important question, and causality really briefly, because oftentimes it's tempting to train a model, maybe it's a complex model, maybe it's a linear model, and then expect the relationships that it finds to reflect the relationships in the real world. But of course, if there's anything that you can gain from a series of interpretability talks about machine learning models, it's all the ways they break and all the ways that they don't reflect the actual relationships in the real world. And so when people train these models, confounders are almost always going to be present. And you have to remember that what you're explaining is the model, not the world. And if your model has not fit the world, then of course it will be different. And these confounders are the types of things that you would hope to identify many times during the explanation process. Because oftentimes confounders are the things that leap out most to human readers, right? Because a human understands a little bit about how you can, a little bit about the world structure. And when they see the model not aligning with the world structure, that's when you can identify confounders. So that's more of a broad thing on confounders and causality in general. If you're interested in causality, then there's lots of great, I think there's econ ML and there's do-y and there's causal ML. There's lots of packages designed specifically for causality, and many of them actually integrate SHAP into them in order to provide better interpretability of the causal models they're building. But it's important to recognize that if you're looking for causality and trying to eliminate confounders, you need to do that explicitly. It doesn't come for free because you're now able to understand the model, even if it's more complex. I'll end on this question here for SHAP for deep learning. I think it's, SHAP for deep learning. How does it best get applied? Well, the tricky part, of course, is we can make these nice arguments for why these SHAP values are really a great way to go about things, but they're super complicated to compute. But we have this great solution for ensemble models of trees and linear models and things like that. But we do not have an exact closed form solution for deep learning models. And what that means is there's a variety of approximations out there. And depending on how you look at it, these approximations can mean different things. So inside the SHAP package, and specifically, we have several explainers that address deep models. First, there's model agnostic ones, okay, and there's ones that are specific to images, specific to text, and there's just model agnostic that take just straight input in a tabular form. And then there's the deep explainer, and there's a gradient explainer. And the gradient explainer and the deep explainer can be viewed as approximations to these Shapley values through some sort of recursive backpropagation methods through the networks. Gradient explainer is, to be honest, much easier to maintain because it is simply dependent on the gradient of the function, and it's related to integrated gradients. It's an extension of that to essentially generalize it, make it a good approximation for our background use cases. And then we also have the deep explainer, which is connected to a prior method called deep lift, which we then said, hey, look, this is actually really connected to game theory as well. And that one works on actually rewriting the backpropagation step and sending credit backwards. In general, deep explainer is much better for high performance, like fast inference, but it doesn't support nearly as broad a set of features at the moment. We're constantly dealing with TensorFlow 1 to 2 kind of changes that make that much more challenging. Gradient explainer works very nicely, but it's harder to push it through things like non-differentiable nodes, which there's no theoretical reason that you can't explain non-differentiable things with SHAP. But of course, if you're relying on the gradient operator, it's hard to override that, and, particularly after people have moved to C++ implementations of stuff. So I would say if you're using sort of tabular data, take a look at both of those. If they don't work, I would then look at SHAP.permutation explainer, which is a model agnostic one that works very well and comes with a lot of optimizations that are new in the last 6 to 8 months. And then we also have, I hesitate to point you to them right now, but very soon we're going to be rolling out a lot of very interesting deep explainers that have specific masking and manipulation methods that are designed for images, text models, and even image to text models or text to text models or text to number, et cetera. So pretty much all the different combinations of model types are applicable, but they usually require a little bit of setup and a little bit of thought about how you mask things. So we're hoping to release a library there that'll make a lot of those much more easy going forward. And hopefully that answers the final question as well, that you can calculate a SHAP value for any type of model, but some models are conveniently, the API is a bit more convenient. So I think with that, I'll pass things on to Rich, who will discuss how to take interpretable models and make them even more awesome.
Thanks, Scott. And if you'll stop sharing your screen, I'll start sharing mine.
Yep.
Okay. Let's see, I seem to be listed as a participant, so I'm not able to share my screen. You guys might have the ability to make me look like one of the co-hosts.
I think
I'm
you're
trying.
now, Rich. I've just added you.
Okay, great. Cool. Okay, let me know if you can see this title slide.
Yep.
Okay, great. Talk about models that are really intended to be glass box. So we've been talking mainly about black box explanation. So I'm going to talk about explainable boosting machines, models that are intended to be interpretable right off the bat. And before I start, I just want to cite a bunch of people who have worked with me on this over the years, 5 great grad students, and also Paul Coach, Harsha Nori, and Sam Jenkins at Microsoft, who have helped build the Interpret ML toolkit. And at the very end, Harsha will give us a quick demo of this Interpret ML toolkit. Okay, so we've been talking about black box explanation. Hey, if you don't have access to the training data, or the model was pre-trained and given to you, or maybe a specific black box model is required, like a neural net or a random forest, or you're trying to understand some complex pipeline from beginning to end, then you really have to use black box explanation methods such as LIME, SHAP, and partial dependence. However, if you're the one who's training the model, you've got access to the training data. And if you're working on tabular data, then you really should be using these glass box learning methods, such as the explainable boosting machine that I'm going to talk about. These methods give you exact intelligibility. They're not approximate. And better intelligibility is going to lead to faster debugging if you're the one responsible for improving the model. So the cycle time is just going to get better. And some of these models even allow you to correct errors and bias that you see in the models. So they let you fix problems, not just understand that the problem is there. Now, you've seen this already in Marco's presentation. We hear a lot about this trade-off between accuracy and intelligibility, that the most accurate models aren't very intelligible and the most intelligible models aren't very accurate. And the good news is that if you're working with tabular data, this is just often not true. That is, we now are starting to have learning methods which are very interpretable, but which also are very high accuracy. In fact, these EBMs that I'm going to tell you about, on a typical data sets, they're just as accurate as boosted trees, random forests, and neural nets. Again, these are tabular data sets, and yet they're even more interpretable than things like logistic regression and naive Bayes. So that's great to have a new class of algorithms that are starting to have all the accuracy and intelligibility that you would want. So here's a study. I'm a co-author on this study. And here for 10 different data sets, we have the average performance of EBMs down here, 0.866. And then for full complexity models, such as random forests and gradient boosting with deeper trees, we see that those models on average on these data sets don't do any better than the EBM does. That is, the EBM gives you all of this intelligibility without any loss in accuracy. Here's a work done by Cynthia Rudin and team. Cynthia is another person who's very well known in the intelligibility community. And what they did was compared a number of interpretable models, and the arrows are pointing to EBMs. And I believe on 9 of these 12 comparisons, we're the best model. On another 2 out of 3, we're the second best. And on one of them, we're the third best. So we're perhaps, the best performing of all the glass box methods. And they observe in this paper that the best interpretable models, that would be EBMs, for example, perform approximately as well as the best black box models, such as XGBoost. once again, an indication that you really can sort of have your cake and eat it too sometimes. And now we're trying to get the same sort of benefit that EBMs have into neural nets. So we're doing some work on what's called NAMs, neural additive neural net models. Sometimes we see a little extra accuracy coming from the neural nets. Sometimes the EBMs are still competitive. So actually it's very close. So I would say that if you have a preference for boosted trees, EBMs are still the things to use. But if you're used to using neural net toolkits and you want intelligibility, there's a chance that you would want to look into these NAMs. Okay, let me explain what these EBMs are. They're a form of generalized additive model, okay? Now, let me just lay out the space here. So here's very simple models. This is an additive model, a linear model. It's a weight times a feature plus a weight times a feature. And then this is full complexity models down here. So just an arbitrary function of all the available features. And there is something in between, and this is an additive model. So this is a function of the first feature plus another function of the second feature. So for every feature, we're going to have a function, and this function can be much more complex than linear, where we just multiply by a weight. These functions can be nonlinear, multimodal, much richer, but they are restricted so that it's only a function of one feature plus a function of another feature. So that's still a great restriction, but it's a much richer model class than linear models. Now we can make that model class a little richer if we want. So this is the sum of all functions of individual features. So that's the sum up above. But if you want, we can include some functions of pairs of features. And now this model could do pairwise interactions. And we could go further and include functions of three-way combinations of features. But what we're going to do is restrict ourselves to main effects, functions of individual features, and a small number of the most important pairwise interactions. And the reason why we're going to restrict ourselves to this model class is, as you're going to see in the subsequent slides, this model class remains very interpretable. Now, we didn't invent these. Generalized additive models were invented at Stanford in the late 80s by Rob Tibshirani and Trevor Hastie. This was Trevor's thesis. But the statisticians were pretty conservative when they fit these models. They tended to use very smooth splines, and they would only include terms in the model if statistics showed that those terms had to be included. Now, a lot has happened since the late 80s. We have a lot more computer horsepower. We have much larger data sets, and we have a lot of new machine learning tricks. So we're going to take this model class that statisticians invented long ago, and we're going to use modern machine learning techniques to get a lot of extra accuracy out of them. And interestingly, when we improve the accuracy, it's going to turn out that the intelligibility increases. And that's for reasons like Scott mentioned in his presentation, that a model that doesn't have the complexity, like a linear model that doesn't have the complexity to represent the data, can actually be less interpretable because it fails to represent the data well. So by making these models a little richer, we're going to get higher intelligibility out of them. And interestingly, we're also going to get editability out of the models, the ability to edit the models and fix repairs. And we've released an open source package about 2 years ago called Interpret ML that makes these models very easy to train. It also, by the way, includes things like Lyman chat. So let me give you a sketch of how these EBMs work. So what we're going to do is a round robin form of boosting. So we go to feature one, we grow a very small tree. This tree can only look at feature one. We have a very low learning rate for this tree. We update the residual, okay, with respect to the original targets that we're trying to predict. Then we go to feature two, we grow a very small tree that can only use feature two. We update the residual again. So this residual now takes into account both what was learned on the first tree and the second tree for the first two features. Then we go to feature three, we go through every feature, and we keep updating the residual and growing a small tree on each feature, but just one at a time. So now one of the reasons we use a low learning rate is we don't want the order of the features to be important. So by using a low learning rate, the later features in the sequence really have the opportunity to learn as much as the early features because the learning rate was so small. We keep updating the residual. So this is a sequential boosting algorithm. And in the end, we've now done one pass through all the features. We have a little tiny tree for each feature, and we have a residual. Learning rate is so small that we're nowhere near done learning yet. So we do another iteration. We grow a second little tree for feature one, continue updating the residual. Second tree for feature two, update the residual. We now have two trees for each feature, and we've updated the residual. We keep doing that for a third iteration, a fourth iteration, and we might do as many as 10,000 iterations. Now we'll use early stopping in a validation set. Maybe it turns out that at iteration 4,000, we sort of hit the peak accuracy on the validation set, and it looks like we're starting to overfit. So we'll stop the process if necessary at 4,000 iterations or 1,000 iterations, or we'll go all the way to 10,000 iterations or more if necessary to do well. Okay, so now what have we got? We have, maybe 10,000 little trees all trained on feature 1, another 10,000 little trees all trained on feature 2. The interesting thing is we can take all the trees trained on feature 1 and we can summarize them as a graph where the x-axis on the graph is just the values of feature 1. So if feature 1 was the age of a person, then we can ask all these trees, what's your weighted vote for age 18? Put a mark on the graph. What's your weighted vote for age 19? Put another mark on the graph, sweep through all the different ages. And now we've got a graph which exactly represents what the weighted vote of all these trees would have been for all different ages. That means we can throw away the trees because the graph now is a perfect summary of what those trees would have predicted. So now we can continue doing this. We can go to feature 2 and we can represent the summary of what all those trees would have predicted just as a graph. Now, in this case, it's a Boolean feature, so it only has the left and the right-hand side here. So in fact, these little trees should only be depth 1. And that's because once you test the Boolean at the root test here, you either go left or right and there's nothing left to do. So ignore the extra depth of these trees for Boolean features. So then we do that for all of the feature columns. So we take all the trees in each column, summarize them as a graph, and then we throw away all the trees. And now we have a perfect summary of what this model has learned in those, what might have been 1 million trees, and how it would make predictions. And what's nice is this summary is very compact. So each graph here is just a 2D vector, right? So it's actually quite fast to use the model. You do a lookup in the first vector, a lookup in the second vector. If you've got 100 graphs, you do a lookup in 100 graphs, add up all the numbers together, and then you're done. So now what would we do with pairwise interaction? So we're going to do something very similar. So what we're going to do first is fit the mains, then we're going to freeze the mains, and then we're going to compute residual effect of the mains with respect to the targets. Then we have an algorithm that will sort through the very large number, order n squared possible pairs. It's going to sort through all of these. We don't want to add, that many terms to the model. So it's going to sort through all of them and just sort of say, these are the ones that seem to be most important. And then the user will say something like, well, use the top 10 most important ones, or the top 25, or the top 50 most important pairs. And then we'll run a very similar round robin boosting algorithm to fit those pairs. And then in the end, the model is going to be the n mains that we trained in the first step, plus the k pairs that we have fit in the second step. So let me show you what it looks like to fit a pair. So the model has told us what pairs to fit. So pair 1 is feature A and feature B. We'll grow a little tiny tree that can use just feature A and B. And then that tree can't use any of the other features, just these two. And it'll probably use A at the root test and B at the child node, or B at the root test and A at the child node. Because most of what could be learned about A or B alone has already been done in the previous step. So now what it's doing is it's mainly learning about pairwise interactions. So then we update the residual just like we did before. We grow a simple tree that can use just features C and D now that are in the second pair. We update the residuals, and we do that for all the pairs that we're going to include in the model. Okay, now again, we're using a low learning rate so that the order we go through the pairs doesn't matter. We're going to go back and do another iteration where we add another small tree for each pair of features. We're going to keep doing that. We might do that again as many as 10,000 times. Again, early stopping will tell us if we should stop after 500 iterations or 5,000 iterations. But then in the end, just like before, now we have up to, let's say, 10,000 trees that have all been trained just on two features, A and B, and we can summarize that now in a plot. Now, this plot is going to be a 3D plot, and that's because it's going to have feature A on the x-axis and feature B on the y-axis. And then the third dimension, which we're representing as a color here, is going to be the contribution to the prediction made by all of these weighted trees. So we sweep through all combinations of values of feature A and feature B, ask these trees what they would predict, and then that becomes a color in the graph. And then once we've done that, we can again throw away those trees because the graph now is a perfect summary of what would have been predicted. So we do that for each pair of features. We summarize it as a graph and throw away the little trees. And then we do that for all the pairs, and then we're done. And now what we have is a bunch of graphs that represent the pairwise interactions, and these are still reasonably intelligible. Now, in the end, what we have is a model which consists of the n main effects, so those are the 2D plots, plus the k pairs that you told the model to use. And these are the pairwise interaction effects. And this is still a pretty compact model. It's a bunch of 2D vectors and 3D vectors. And that's all the model needs to do is do lookup in these vectors when it needs to make predictions. Okay, now I'm going to jump in and just sort of show you the kind of things that we can learn from these, and they'll help you better understand what these EBMs are good for. So there's a bunch of case studies. I won't do all of them today. At least two of them, the one on pregnancy and the one on COVID-19, I'm going to defer until the presentation that I'm giving Thursday, I think at like 11:40 in the morning. So that talk is going to focus more on explainable machine learning for healthcare. So I'll reserve these for that presentation. And if we start to run out of time, I'll also reserve the 30-day hospital readmission for that. Okay, we'll spend a little more time on pneumonia. I apologize, some of you may have seen this before, but I won't spend the entire talk on this. But this is a good one to sort of help you understand what EBMs can do. Okay, so this is a data set from 1989. It had 46 features in it. And think about the model class. It's a function of a feature plus a function of a feature. 46 features, we're going to have 46 functions. And then we're going to throw in 10 pairwise interactions. So we'll actually have a total of 56 functions. And you already saw some of these pairwise interactions. They were the ones that were at the bottom of my slide a few slides ago. So let me show you what this might look like from a high 30,000 foot level view. So here's a function of the patient's age. Here's a function of if the patient has asthma or not. Here's a function of their blood glucose. Down the bottom, a function of their blood urea nitrogen. Remember, we've got 56 functions, graphs like this. And the way you use it is you find the patient's age in this graph, and then you write down the Y value, maybe minus 0.23. If the patient has asthma, you write down the Y value, maybe minus 0.15. It's an additive model. You're going to get 56 numbers like this, and you add them all up. And the more negative the numbers, the lower the risk, and the more positive numbers, the higher the risk of the patient. In this case, we're trying to predict the probability of death of the patient from pneumonia. So how risky is their pneumonia? So we get a score like this by looking at all 56 plots. And then to convert that to a probability of death, you just do the standard logistic trick, 1 over 1 plus e to the minus score. Now, if this had been a linear model, linear regression, logistic regression, this score would just look like a linear model here. It would have an intercept plus a weight times the first feature plus another weight times the second feature. This would just be a linear model. What makes this more flexible is that instead of this being a linear model, we actually have a nonlinear function of every one of the features that's contributing to the score. And that makes a big, big difference in how accurate the model can be. There are many things linear models can't do that this model can do. Now, we take the sum of all these predictions. That gives us a score. Maybe for this patient, the score is minus 0.78. And then that would turn out to be a probability of death, which in this case is very high, probability of death of about 30%. You'd really like to be a -2 or a -3. And that's important to understand that the scores that are coming from these graphs are on a log scale. So a difference here of +1 increases your odds ratio by about a factor of 3, by a factor of E. And a -1 on one of these graphs is a huge reduction in your odds ratio by, again, a factor of E, by about a factor of 3. So you got to think of these graphs, a difference of 0.5 in these graphs is a big deal because it's a log scale. Now I'm zoomed in here on the graph of what we've learned about risk as a function of your age. This is pneumonia risk still. At the bottom, we've got a histogram of our patient population. Most of the patients are between 60 and 90. These are all in the hospital. Some of the patients are 20s, 30s, and 40s, and a few patients out near 100. And let's interpret this graph. Remember that down is lower risk and up is higher risk. So the model is saying that basically everyone under 50 is equally low risk. It doesn't seem to distinguish between anyone between 20, 30, and 40, even though it could if it needed to. And then risk goes up sort of slowly as you go through your 50s into your 60s. Pretty rapid rise in risk right around 67, 68, 69. That would be retirement age for this data set. We see this, by the way, in a lot of medical data sets. You might hope that retirement would be good for your health, but in fact, at least in the US, we often see that retirement adds a little bit more to your risk. A lot of things change at retirement in the US. Your insurance payer probably changes. Your provider might change. Maybe you've even retired and moved someplace where your doctor has changed. So you're maybe just not plugged into healthcare as much as you were before you retired. Risk goes up pretty rapidly as you go through the 70s and into your 80s. That's normal, right? You're becoming elderly. Interesting step function rise in risk right at 85. That's sort of weird. Risk is pretty flat through the upper 80s and 90s, and then a really surprising drop in risk that's happening right around 100, 101. Now, this rise at 85, we're pretty sure that's what's happening is, remember, this is a data set from 1989. Average life expectancy might have been around 80 years back in 1989. So if you're over 85, you're definitely on the elderly side of elderly. And we think what's happening is doctors are giving little less aggressive treatment to patients who are considered very elderly, patients over 85. And they're giving, more usual treatment, more aggressive treatment to patients who are under 85. And we think the doctors are just using a sort of round number to help distinguish, what would be extra elderly patients from patients who are not quite so elderly. And back then, pneumonia was sometimes referred to as, the old man's best friend. The idea being that you have illnesses, comorbidities associated with being elderly. And that's probably why you have pneumonia now. And that, the pneumonia is likely to take you out within a week or two because it's a rapidly advancing condition, unlike the underlying comorbidities that may have caused you to get pneumonia. And that maybe it was a friendlier way to pass away was to die quickly from pneumonia than to be allowed to sort of linger for months or even a year or two. And die from the other illnesses that are associated with being so elderly that you have, which is why you've got pneumonia. So this drop at 100, though, that's even more interesting than this rise at 85. And we think it's a social effect, just like this rise at 85. We think that what's happening at 100 is that, at 85, maybe we're going to give little less aggressive treatment to patients over 85. But if you've made it to 100, 101, we don't want to give up on you. And pneumonia, after all, is a fairly treatable illness. So basically, if you've got pneumonia and you've made it to being a centenarian, we're not going to give up as easily. And we're just going to sort of keep fighting. If you need that third round of antibiotics, we're going to do it. And we see a sign that, in fact, this extra aggressive treatment that the people over 100 receive is effective, and it actually lowers their chance of dying. And when I give this presentation to a medical community, invariably a doctor or two comes up to me afterwards and says, that's exactly correct, that we tend not to want to give up on people who've made it to 100 if it's a very treatable illness. If it's not a treatable illness like terminal cancer, well, then that's different. We might not decide to continue to fight so aggressively to save their life since the end is near anyway. Okay. Interesting thing about this model, it's got all sorts of detail: flat risk here, low risk here, retirement effect, risk as a function of becoming elderly. Over 85 is a little bad for you because maybe we treat patients over 85 a little less aggressively, at least back in 1989. And then being over 100 is good for you because you really get special attention over 100. There's 56 graphs. Almost all of the graphs have interesting stories like this. We can really understand a nuance of how the model has learned, and it's fascinating. However, this model is just as accurate as any other model that can be trained on the data. It's the most accurate model on this particular problem. So it's more accurate than a neural net, random forest, boosted trees. So it's a great model. We got all of this interpretability without losing any accuracy. So that's really fantastic. Now, one of the things that this interpretability gives you is the ability to look at this and say, wow, do I actually like what it learned? So an interesting question is, would we want a model to predict that people who are 105 are lower risk than people who are, say, 95? If they're only lower risk because they got extra aggressive care, but not because they're intrinsically lower risk. Maybe we want this model to be predicting more about intrinsic biological risk so that we can base care decisions on it. So one of the things we can do with this kind of model is we can edit it. And if we edit it, for example, we can make risk be a monotone increasing function above, say, 85. And because the model, in the end, we delete all the trees, and in the end, it is a series of lookup vectors of graphs. If you edit the model, it will have to do what you say. By the way, when we edit the model this way, you have to be careful. You're overruling statistics in the data. So you always want to do that cautiously. Also, the accuracy on the test set will actually go down a little bit. And that's because the statistics that are true in our training set are also true in the test set. The test set is just a sample from the training set in this case. So it turns out that by editing the model to say higher risk above 100, it'll actually be a little less correct on the test data, but we believe it'll be more correct, safer to use if we were to deploy the model. So we're actually willing to accept a small loss in accuracy on the test set because we actually think the model will be more accurate when we use it in the real world. Okay. Would you always want to make that edit? It turns out no. If you're an insurance company and your goal is just to understand if a patient is going to live or die, you don't really plan to intervene in their healthcare. So it's not like you're trying to predict their intrinsic risk. You want to predict the risk after the care they're going to receive. So as an insurance company, you want to leave this the way it is so that you can understand that patients who have pneumonia who are over 100 are actually a little more likely to survive than patients in their 90s. You need to keep more money in the bank for these patients because they're a little more likely to survive than somewhat younger patients. So if you're an insurance company, you don't want to edit the model at all. And yet, if you're going to use the model to predict patient risk, you need to edit the model. That's one of the most important lessons we found from interpretability, is that the correctness of a model and the accuracy of the model depends very much on how you're going to use the predictions from the model. An insurance company will use the predictions very differently than a doctor would use the predictions. And because of that, in one case, we need to edit the model for the doctors, but not for the insurance company. That's very, very important. Let me show you some things that the model has learned. We see lots of jumps at round numbers. I'll show you one or two more of them. They're almost always due to human social policy effects. There's very few phase changes that happen in biology and physics. The model learns that asthma is good for you if you've got pneumonia. That is, having asthma on the right here lowers your risk. The explanation for that, we think, is that asthmatics notice the symptoms of pneumonia earlier. They have a med like an inhaler. They try it. It doesn't seem to work. They have a doctor who treats their asthma. So they call the doctor. The doctor says, oh, the inhaler didn't work. Get in here. They get really rapid access to healthcare. And then the doctor diagnoses that they've got pneumonia. They're considered actually to be higher risk because of their history of asthma. So they get really high quality care. And if you've got pneumonia, it's very, very important to get to high quality care quickly. So these patients are actually lower risk than patients who don't get to care as quickly because they got to care so fast. Now, it turns out that having heart disease and chest pain are also good for you. So if you've got pneumonia, right? And that doesn't seem to make any sense. And we think it's the same explanation as this asthma explanation. So you have a history of heart disease, you start having a funny problem in your chest, you think you might be having a heart attack. If you're smart, you get to the ER in an hour. You get there incredibly quickly. They determine that, no, it's not a heart attack. They determine that, in fact, it's pneumonia. Because of your history of heart disease, they consider you to be higher risk. You're already probably in the ER. So you get incredibly rapid and aggressive treatment. And that treatment is so effective that it really lowers your risk. And there's actually two graphs that look like this, and it's an additive model. So heart disease really lowers your risk quite a bit, almost minus 0.4, more than asthma does. There's something that's even better than asthma and heart disease, and that's to have a lung obstruction, which causes you to wheeze in a certain way. This is a sign that your pneumonia is actually quite advanced. And the reason why this is good is similar to these others. What happens if you have this kind of wheezing, you know you are very sick and that you have to go to care. You sound terrible. And anyone in the room who can hear you knows that you're very sick and will tell you you have to go to the hospital. So they will force you to get care. If you're going to have an illness like pneumonia, it is better to have symptoms that are very visible than to have hidden symptoms. And Stridor, this kind of wheezing is one of these very visible symptoms. Okay, now, it's an additive model. And it now predicts that a person who's 105, who has a history of asthma, history of chest pain, history of heart disease, who now has an obstructive lungway, is actually very low risk. We probably don't want the model to do that. So what are we going to do to fix this? Well, one of the things we can do is we can just make all these effects go away by zeroing out the graphs, just draw them as a zero. And now the benefit or harm of having asthma or heart disease just goes away. Or a doctor could tell us, no, the asthmatics are actually at higher risk, despite what the model has learned. I want you to increase that risk 0.38. I want a 0.6 for the people who have heart disease. And for Stridor, that's terrible. It means their pneumonia is advanced. I want a plus 0.8 for them. And if this is what the doctor tells us to do, we can do this. The interesting thing is the accuracy, again, will go down on the test data when we do this. And that's because the test data looks like the training data, and the training data was telling us that all of these things were good for you. But there's something even worse than the fact that the accuracy is going to go down on the test set. And that's the fact that the model was rewarded with what looked like extra high accuracy in the first place for predicting these wrong things. And this sort of drives home this idea that accuracy is not the single determiner of whether your model is good. A more accurate model is not always a better model. In many cases, the models learn things like this, which are actually wrong, dangerous, and need to be fixed. Now, there's another way you might think you could fix this. You might think that you could remove features like asthma and heart disease from the model, and then it just wouldn't be able to predict that heart disease patients were lower risk because it wouldn't know that they had heart disease. There's a problem with that, which is that the bias is actually coming from the training signals, not from the input features. Input features, if measured correctly, are just facts about the world. They're not biased. But there's going to be correlation between the input features. And even if you remove heart disease, through correlations with other features like age and blood pressure and things like that, it is going to try to get its heart disease is good for you fix. And it will now spread the effect as much as it can among all the correlated features. And that's terrible because, one, you probably won't be able to see that it is learning that heart disease is good for you because it's now spread on these other features. And even if you knew it was there, it would be much harder to figure out how to correct it because it's now spread throughout the entire model as opposed to localized on something like a heart disease graph. So now what we do when we're afraid of this sort of bias, these kind of errors that a model would do, maybe we're afraid of race bias or gender bias in a model, we make sure that race and gender are included as input features to the model. We let the model learn to be as biased as it possibly can be. And then we can see the bias that's in the data and we can correct it by editing the graphs. Let me show you, not everything that machine learning models learn about data is bad. In fact, 95% of what they learn is good. So this is a wonderful graph. This is pneumonia risk again. This is your blood urea nitrogen. This is a blood test all of us have received. And doctors really love this graph because they could see the treatment effects. They could see the benefits of their treatments. So doctors start to treat high BUN with a med somewhere around 50. And you can see that the graph flattens off right around 50. So that's because their med is useful. And then doctors start to treat more aggressively with dialysis at 100. And you can see right at 100, risk starts to go down. And that's because by 110, almost all the patients are getting dialysis. But doctors were also sort of saddened when they saw this graph because they realized risk was very high at say 35 or 40. And they wondered if they shouldn't change this treatment threshold to being earlier, say 35 or 40. And here it's particularly bad. Notice that the sicker patients who have a BUN of 110 are actually lower risk of dying than patients who are healthier with a BUN of say 90. So that's really sort of unfortunate. And doctors wondered if this treatment threshold shouldn't be moved to 85 or 90 to prevent this from happening. So with this kind of additive model, we can treat it almost like a spreadsheet. And we can conservatively draw that if we change the treatment threshold for dialysis from 100 to say 85, that the graph would now look no worse than this red line. In fact, it would probably go under this red line. And then the area between the red line and the original curve, these are lives saved. So it turns out our estimate is that just by changing this one treatment threshold from 100 to 85, for just one blood test, blood urea nitrogen, for just one condition, pneumonia, which is a common condition, that in the US alone, we might be able to save 2,500 or more lives. And if you think about it, you shouldn't be surprised that we would want to move the treatment thresholds once we saw good data. And that's because what are the odds that 50 was the right treatment threshold for the med, and 100 was the right treatment threshold for dialysis, right? I mean, the odds of round numbers like 50 and 100 being the right answer is near zero. So it makes a lot of sense that maybe the right treatment threshold is 35 to 40 here, and maybe 85 to 90 here. Treatment effects are all over in medical data, so we deal with them all the time. This is systolic blood pressure. This is good blood pressure down here. Notice there's a rise in risk right around 150, a rise and drop that's happening near 175, near 200, near 225. All of these things are happening near round numbers, and that's because doctors are using round numbers to make their medical decisions. And we often see these treatment effects, and we have to reason about whether to leave these treatment effects in the data or whether they need to be corrected, or whether maybe healthcare can be modified to benefit from what we've learned from the models. Let me show you a pairwise interaction. This is risk as a function of age, that we saw that before. Risk is a function of cancer. Cancer adds to your risk. But there are some things you can't model as a risk from this graph plus a risk from this graph separately. If you think about parity or exclusive OR, you really need to know both bits at the same time to be able to predict something. So that's what this graph is. It's one of the 10 pairwise interactions. This is age on the vertical scale and whether you have cancer or not on the x-axis. And I just want to draw your attention to this yellow at the bottom right. This is adding 0.5 to risk on a log scale. That's adding an awful lot to risk, okay? And why is it doing it? It's doing it for very young patients, which is kind of unusual. Remember, young patients are the low risk patients. And we think what's happening is the model is basically saying, we have patients who probably had cancer either in their late teens or now in their very early 20s. We're giving them very aggressive treatment. We treat young cancer patients more aggressively than older patients because the younger patients can survive the treatment. And that aggressive treatment often knocks out their immune system. And because we've knocked out their immune system and they now have pneumonia, they're actually at extra high risk because their immune system is not there to help them. So the model is basically singling out what is a very sad story, that there's a very special class of very young patients who are at extra high risk. So let me show you some stuff from the MIMIC ICU mortality data set. And this is just interesting from a model debugging point of view. This is PF ratio. This is how well you're converting oxygen in the air you breathe into oxygen in your blood. And low PF ratio is bad. You're having trouble breathing. That's a +1. That's a big deal. Whereas most of us who are healthy are over here at around 1,000. And the interesting thing is this funny blip that's happening right here. I mean, what is going on? Why is there a group of people who look like they're low risk right at this place in the graph? So our first thought was, well, maybe it's a round number, but it turns out it's 323. That's not a round number. We thought maybe it was a round number in metric units, then converted to English units. No, these are the natural units, so that's not it. We started fishing around, and one of the things we looked at was what's the mean value of this feature? And it turns out the mean value of the feature falls right here at 323. So that's very interesting that this blip is happening right where the mean is. And our next question was, were there ever missing values in the data? And if so, might they have been imputed in the mean? And it turns out that is the right answer. So it turns out that about 60% of the patients have never had their PF ratio measured. That's because we assumed that they were fine. They did a pinch test and everything looked good. Those patients were then imputed accidentally, I would say, by using the mean value. That puts them over here in a higher risk part of the graph. And the model is doing what it can to predict that these 60% of the patients are actually low risk. And this would be fine. It doesn't hurt the model accuracy too much. But what's bad is there are some patients who really have a PF ratio of 323. And because they're being surrounded by patients who are very healthy with that imputed missing value, it turns out they're being predicted as being low risk when in fact their risk is considerably higher. So what we need to do is detect this sorts of problem and then fix it so that the patients are not being predicted as being low risk. I'm going to skip this and go on to this German credit data set. This is a data set where we have a bunch of German nationals and German foreigners who have been given a loan, and we're looking at the risk of them defaulting on the loan. And here's one of the graphs. It turns out that the longer the loan duration, the higher risk. That makes sense. And it's a big difference, minus 0.5 to plus 0.5. That's a factor of 3 to 1 in odds ratio. Here's something interesting. The foreign workers, as expected, have higher risk than the German nationals for a loan in Germany. I guess that kind of makes sense. Here's a real surprising thing, though. The error bars for the foreign nationals are huge, while the error bars for the foreigners are very small. And that's weird. You would expect larger error bars actually to be on the group that has the higher risk. So that's kind of strange. And we looked into the data, and it turns out that 98 to 99% of the people are actually foreign nationals, and only 1+% of the data is German nationals. So it's pretty clear this data set was never intended to have German nationals in it. It was really a data set that was meant to look at foreigners, and somehow a few people labeled as German nationals got into the data set. So that was our first sign of problem. Then we looked at this graph. This is risk of the loan as a function of the size of the loan in Deutschmarks. And notice there's a rise in risk right here at around 4,000 Deutschmarks, which isn't a huge amount of money. And the interesting question was, why would there be such a large increase in risk right at this amount? We did some searching. This took some detective work. And it turns out at the time of German reunification, when East Germany was joining West Germany, it turns out that loans, dollar amounts under 4,000 were converted to West German Deutschmarks 2-to-1. That is, they were trying to help people from East Germany by giving them a very favorable conversion rate on their Deutschmarks for the first 4,000. After 4,000, though, they were only converted 1-to-1. And we think what this did was it led to a distortion in the lending characteristics of the East Germans who were trying to get loans of exactly this amount so that they would benefit from the favorable conversion rate. But what this tells us is that this is a very unusual data set. It's really intended to be looking at credit risk for people who were East Germans, possibly at the time of West German unification. And sure enough, it turns out when we do more research on the data set comes from within a year of East-West German reunification. So again, it's these sort of details we're seeing in the models, including the error bars, that are causing us to do good detective work on these models. So I'm going to show you some work we've done with Wikipedia. So Wikipedia, there's a couple 100,000 edits per day, maybe 10% of which might be malicious or damaging edits. And editors spend time looking at these things. And it's not possible for them to look at all edits. They don't have the manpower to do that. So they train models to try to predict which edits are most likely to be malicious. And then this is a model, an interpretable model we've trained for them. And this is just one of the graphs. This is the graph, the number of seconds since the editor signed up to be an editor. And I just want to show you some details that the model learns. This little blip happens at 9 months. That happens at 1 month. That happens at 5 days. That happens at 30 minutes. That happens at 60 seconds, 30 seconds, and 5 seconds. So the fact that we see jumps in the graph at all these round numbers is a sure sign that we're looking at social human behavior. And let me just explain one of these to you. I'm going to explain to you what's happening at 1 month. So it turns out if you've created an account with Wikipedia, they have a policy after 1 month, they log you out. And that means if you want to continue editing, you have to remember your password and log back into that same account. And notice that this greatly lowers your risk if you're beyond 1 month, because you really have to remember your password. I mean, you had to be somewhat serious about creating this account, whereas the risk of malicious edits is much higher for people who are less than 1 month. And we think Wikipedia could help themselves, perhaps, reduce the number of malicious edits by just changing this policy from being an auto log out at 1 month to maybe being an auto log out at 1 week. And that maybe it would move this low risk region over further to the left here. Okay, maternal morbidity, I'm going to talk about that on Thursday. COVID-19, we are able to do things like see what are the big and small risk factors for COVID-19. I'll show you that as well on Thursday. This hospital readmission, I think I'll reserve that also for Thursday. And then I'm going to wrap up with just one more use of this kind of explainable model. And now what I'm going to do is do black box explanation, but using a glass box model. And what we're going to do is we're going to open up the black box to see what's going on inside of them. We're going to use this Compass data set you've probably heard of. It's a black box because it's protected IP, not because it's actually a complex model. And this model is used in the US to inform decisions about bail or parole. And there's been a lot of papers published suggesting that this model is racially biased, which of course is a problem. So we're going to follow up on that work. Now, the way we're going to do this is we're going to take the black box Compass model, We have 10,000 people who have gone through this model. We know what their predictions are, and we're going to train an interpretable model to mimic those predictions. And if this is a faithful mimic of the black box, understanding this model should help us understand the black box model. This is kind of like what's also happening with SHAP and LIME. We're training one model to mimic another model so that that model can tell us about the original black box model. Now, here's risk as a number of prior convictions. And first of all, notice that risk goes up dramatically if you have a large number of prior convictions, from -1 to say +2, 3, or 4, right? This is a log scale. Plus 3 or 4 is like a 50 to 1 increase in the chance that you're going to recidivate. The green score is actual recidivism data that we have for these 10,000 people. So that's what we learn when we train on the real signals. And the red score is when we learn to mimic the compass model. And notice that we learn essentially the same thing when we're mimicking the model or when we're learning from the raw data. That's a really good sign. It's a very good sign, first of all, that Compass probably did a great job of modeling this feature. It's also a good sign that we're probably doing a good job of mimicking the Compass model because we think we're learning what they probably did with this feature. But now this is what everybody talks about. This is race. So the interesting thing is the Compass model, remember, pink is when we mimic the Compass model. Green is when we looked at the raw scores. The model seems to predict higher risk for African Americans than the data actually suggests is warranted. And yet for white Americans, the Compass model seems like it predicts lower risk for white Americans than the data even warrants. So this is a bias of two different forms. First of all, we're just predicting higher risk overall for African Americans than for Caucasian Americans. But also what makes it even scarier as a bias is that, and we're predicting higher risk than the data seems to warrant for this group, and yet we're predicting lower risk than the data seems to warrant for this group. So that really is an indication of the racial bias that many other researchers found before us. But here's something those other researchers didn't talk much about, and that's that the model seems to be very biased against Native Americans. This is a +1, that's a huge deal. And yet the data for Native Americans, if anything, suggests that they might be lower risk. So the model is actually much more biased for Native Americans than it is for African Americans. And we think people don't talk about this because they weren't training an interpretable model. They didn't know to look for it. And we think the explanation for this is that the Compass model was probably trained on Native Americans from around the US, whereas the 10,000 people that we have to test these models and train these mimic models is only from Brewer County in Florida, very localized place in Florida. And we think what happens is Native Americans in Florida, this green, look very different from Native Americans perhaps in the rest of the country. We also think the Compass model might not have put in as much diligence to prevent Native American bias as we believe they put in to prevent black-white bias. Now, this is black box explanation, but using an EBM as opposed to SHAP or LIME. Now, both of these methods can be expensive because effectively, we're both trying to form an approximate model of the black box, and that can be time consuming. Now, EBMs, they're exact when we use them as a glass box model, but they are no longer exact when we explain this sort of black box. Now, if it turns out that the EBM, which is mimicking the black box, is accurate enough that you want to use it as the model you deploy, well, now it is an accurate explanation of the model you're going to deploy. But if you deploy the black box, this is still an approximate explanation of what's going on inside that black box. And EBMs and SHAPs make different assumptions. SHAP is based on game theory, so you can make proofs about some of the properties of SHAP, whereas EBMs is just round robin gradient boosting. So we can't really make any proofs about this. Now, there are different strengths and weaknesses to these things. So you wouldn't necessarily always prefer one to the other, but note that SHAP is at least theoretically a little more sound than EBMs might be when trying to do this black box explanation. SHAP, however, usually assumes you have access to the black box. And because of that, it demands that you can probe the model multiple times. But because of that probing, it actually is more likely to tell you what are the correct features that are being used in the black box model. But SHAP, for example, can't be run on the ProPublica data, and that's because we don't actually have access to the Compass model. We only have access to the predictions from the Compass model. We can't repeatedly probe it anymore. Now, SHAP, therefore, can't be used to detect this residual bias we found, like the black-white bias and the Native American bias. And that's because we can't use any features in SHAP that weren't used in the original model, in the original black box model. We believe the COMPAS model does not use race as an input feature, but that doesn't mean it's not biased. But by using race as an input feature in our mimic model, we're able to detect some of that bias. And sometimes this extra flexibility that comes from using EBMs instead of from using SHAP is useful. Pairwise interactions aren't exactly a first-class citizen in SHAP, but they are in EBMs. In SHAP, they create that vertical dispersion, which is useful. And in fact, I like the SHAP plots a lot. That vertical dispersion is very telling. But you can actually learn more about the pairwise interactions if you train an EBM model. So the methods are just different in how they handle and then present to you pairwise interactions. SHAP, LIME, and EBMs really have complementary strengths and weaknesses when being used to open up a black box model. We encourage you to use both whenever possible. And our package, the Interpret ML package, makes it easy to do that. Just going to wrap up. Intelligibility explanation, very, very important. And by the way, if you're just a data scientist who's got to train an accurate model next month, they really help you debug your data. They'll help you build trust in the model before you deploy it. And they'll even help you learn things that will help you improve the model accuracy. If you must use black box explanation, then LIME, SHAP, partial dependence are the things you probably should use, although you can use this distillation method with EBMs, which in some settings will give you some extra utility that you wouldn't have with LIME and SHAP. If you're the one training the model, though, you've got the data, you really probably should be using glass box models, especially if you're working on tabular data. As Scott said, these glass box models still lag behind the accuracy of like deep neural nets on things like pixels and raw speech and massive text. But when you're working on tabular data, there's often no loss in accuracy. And sometimes, in fact, the glass box model like EBM is even more accurate, as it was in the pneumonia case. Okay, we're going to pass it over to Harsha, and he's going to tell you about this Interpret ML package. I'll just briefly take one or two questions, but then I want to give Harsha time. So maybe I won't do too many questions. And if you've got questions, and they might even be relevant for the medical stuff, if you come to the talk Thursday, you can also ask them there if you don't get to ask them here. So thank you. So I've stopped sharing my screen, and if there are some questions here, yes, the talk is recorded. Go ahead.
Do you mind seeing if you can make me a host again? I think I lost it, so I might not be able to share my screen.
Hey, Dave, if you're listening, are you able to make Harsha Nori a host?
Absolutely, Harsha, you should be good now.
Perfect. Thank you.
Okay, great.
Sorry
great,
about
great.
that.
Great. No. Good to have asked that question quickly.
And if we do run 15 minutes over, so we should be okay with the Zoom link. I don't think it's going to cut off.
Okay, so I'll take a few questions if there are questions, and then we'll still try to get to Harsha in 5 minutes or so.
Yeah.
Let's see. So I don't know how far back I need to go. Maybe I'll start from here. Oh, by the way, somebody says here that they'd love to keep in touch. They said that privately, but I'll just say publicly that we're all happy for you to get in touch with us, especially if you're trying to use LIME, SHAP, or EBMs on a hard problem. We're happy to help you as much as we can. You know, in some sense, the textbooks on these methods aren't completely written, so we're happy to fill in and help you. And this is work we're all working to improve these methods. So often when we see problems that you're having, it also helps inform us about what we should try to do next. So feel free to get in touch with us. Also, if we don't get to answer your question today, of course, feel free to ask us your question. Let's see. So can you test your own features with EBMs like TCAV does for deep nets? That sounds interesting. So one of the nice thing about EBMs is that the features that are in the model does not have to be only or all of the features that were in the original model that you might be trying to explain. So it's very easy for us to have signals that came from a model using some set of features, possibly a deep net in pixels. And then if you can create interpretable features from that, say using TCAV or superpixels like Marco was showing, then we're able to do EBMs on top of these other features, the things like superpixels. And then the explanation can be in form of all these other features that you have available. So that is one of the benefits of using EBMs, I guess, compared to SHAP specifically, is that we can use any features you can provide to us, whereas SHAP is trying to be very careful and make sure that its explanation is only in terms of the features that were actually used by the black box model. That's a really good property of SHAP, and it's one of the reasons you can prove theorems about SHAP. But it is also one of the things that maybe reduces some of its flexibility. And in some settings, you might prefer to use an EBM instead. Question here about EBMs available in Spark. We're actually doing work right now to try to get EBM available in Spark. I wouldn't say a month, but it's probably a few months away. We also have a very early version of EBMs in R. It doesn't have all the capabilities of Interpret ML, but it does give you the very basic capabilities so that at least you can sort of sample it. If you're an R person, you can play with it in R. And then you, if you like it, if you get hooked on it, you may want to switch to Interpret because that's a more feature-rich package. Currently, have parallel cores on single machines. Oh, wait, that's an answer from Harsha. That's
yeah,
great.
that's me.
Oh, and the best way to get in touch with us probably is through email. And if you want, another way to get in touch with us is, for example, if you go to Interpret ML on GitHub, you can even contact us through the GitHub package. And I think the same thing would probably work for the Lime and SHAP package. And Interpret ML incorporates also Lime and SHAP. So if you send us a Lime or SHAP question through Interpret ML, we'll try to make sure that it gets to Marco and Scott. Okay, it looks like the end of the questions, and that's about 5 minutes. Let me try to hand it off to Harsha so that we don't run too late and trash all of your schedules. Thank you very much for listening to the presentation. And now Harsha is going to give you a quick demonstration of how all of these things are integrated into this one package and sort of show you that we're trying to improve integration going forward. So go ahead, take it over, Harsha.
All right, perfect. Thanks, Rich. I'll post a generic email in the chat. I see a lot of questions about emails. We have a shared email address that will reach most of us at the same time, and we can always forward it as needed. So if anyone has like direct questions, you can always contact us at interpret@microsoft.com. And of course, like we can probably find ways of sharing Rich, Scott, and Marco's emails directly too. But in the interest of time, I'll just start doing a little bit of a live demo. I'm just going to walk you through some Jupyter notebooks and show you just kind of how the code works, how you can run it. If you've been excited about any of the things you've heard, this is the part where we translate that into how you can use it on your own problems. So let me share. And Rich, if you're still there, could you confirm that you can see the screen?
Yes, your screen looks great.
Okay, perfect. Thanks. So everything I'm going to talk about is from the Interpret ML package. You can visit our GitHub URL, github.com/interpretml. Rich has talked about how we released this a couple years ago. There's some like documentation on the README, but perhaps more importantly, I'll be walking through this set of example notebooks that are posted there. So if you want to copy paste this code or reuse it or just look at these notebooks, they're all found on our GitHub page. And with that, I'll be moving pretty quickly through this. I just want to give you an intuition about what the package can offer for you and some basic guidance on how to best use it. So at the beginning here, I'm just setting up a very simple machine learning experiment. I'm downloading the adult income classification data set from the UCI repo, making sure the column names are right, and creating a training set and a testing set, just so we have a way to test our model's validation. And then the main kind of paradigm inside of Interpret is the idea of explainers and explanations and kind of how you get visualizations from those. So the first kind of concept is we provide some utilities to look through your data set. Interpretability doesn't really mean much outside the context of the data you're working with. So kind of like a scikit-learn style method, you initialize a class and then you can call explanations from those classes. So here we're just trying to explain our data with simple histograms, right? And we see that there's features like age that have different proportions of positive and negative samples inside these bins. We've got some categorical features like the marital status of the people. This is the income classification data set that Marco referenced in the first talk. And the goal is just to predict whether or not people have a high or low income. So outside of that, we just spent some time hearing from Rich on explainable boosting. And if you want to use explainable boosting machines, the interpret packages house the main implementation of those. They're all hosted inside of this Glassbox namespace. So this is the kind of idea of intelligible models. And outside of EBM, Interpret also implements logistic regression, simple rules, decision trees, just many other kinds of Glassbox models too, that all follow the same API. So training an EBM is the exact same as training any of these other Glassbox models. I'm just going to use an EBM for demo purposes. And if any of you have seen scikit-learn or played with it before, like the API is exactly the same. You initialize a classifier or a regressor, and you fit it with your training data and your targets. Where we start to break away from scikit-learn is, again, the idea of explanations. Because EBMs are kind of an interpretable model, they have facilities to provide their own explanations with this explain global function. And if you're using these inside of a Jupyter-like environment, whether it's actual Jupyter notebooks or inside VS Code or SageMaker or whatever, we've got this kind of magic visualization function called show that'll create like a nice little widget for you to play with and help understand your explanations. So you'll get back kind of an overall feature importance score at first. But just like Rich was talking about, you can drill down into any individual graph. You can zoom in and export these to PNGs. There's a lot of nice little utilities in here that make it kind of easy to look through these graphs and learn the kind of insights that Rich was talking about. And again, the same is true for categorical features, and you'll see the corresponding error bars, and you can always hover to get the exact values. The same is true for local explanations for any kind of Glassbox model. You can look at any individual prediction and you can see kind of that breakdown of where the prediction's kind of composition was coming from. So in this case, this person's predicted as having a really high income because they made $28,000 in capital gains, which, makes sense. We have some utilities to help evaluate model performance and kind of prove that Glassbox models can do just as well as black box models. So we encourage you to try it out and run the comparison for yourself. And of course, just like we fit an EBM before, you can do the same with things like logistic regression with whatever kind of parameters you want to set for that. Same with simple decision trees. And now start to kind of compare their performance using the tools that we have built in. So one last thing to call out is, we have tree visualizations, anything you might need to really help work with Glassbox machine learning. And we also include a dashboard that you can create that really kind of helps you compare different methods together. So the goal of Interpret is really to provide implementations of many different Glassbox models and black box explanation techniques, and then help you pick the best one for your problem. Maybe an EBM is best in your situation. Maybe simple rules are easier to understand for some of your customers. It all depends on what kind of situation you're working with. And we just want to help provide the tools and the comparison framework for you to be able to pick which one you want to use. So for example, if we want to compare how a logistic regression did with an explainable boosting machine for these global explanations, we can see how they learn different things on each individual feature. And as you can see, like the logistic regression and the explainable boosting machine have a very different model representation. Though because this is a linear model, it's only allowed to learn an ever increasing contribution of the age feature to the final prediction. So this logistic regression model by design is restricted to think that the likelihood of having a high income goes up monotonically with age. Whereas the EBM's allowed to learn something much more nuanced and detailed. It's allowed to learn that income is flat in your early 20s, it rises until your mid 40s, and then kind of drops off and stabilizes after retirement, right? So already you can kind of start to see the differences between these models. And this kind of comparison can extend in many, many different domains, comparing different black box explainers. If you want to see what changes between a SHAP explanation and a LIME explanation, the same kind of dashboard and framework is there to help you make those kinds of comparisons. Okay, so that's a whirlwind tour of Interpret ML. The big takeaways are we've got a nice simple API. It's a heck of a lot like scikit-learn. And we've got visualization tools that encapsulate all of these different methods and make it easy for you to compare them. And if you have any questions, please feel free to send us an email or visit the GitHub page. I do want to spend just a few minutes, if people can stick around, talking about kind of the next generation of where Interpret ML is going, since it's been around for a couple years now. And so this is all joint work with Scott and the SHAP package. And we've been spending the past 6 months or so really thinking hard about what is a kind of a nice API for interpretability and explanation. And over the next couple weeks and months, you'll start to see both packages work more harmoniously, closer together. So what we've done is we've created kind of a shared explanation object and a shared explainer API that we're calling the Interpret API. SHAP has already started to adopt this. You'll see this in Interpret ML soon. But effectively what this means is that if you generate an explanation using the SHAP package and you generate one using the Interpret package, they'll be returning effectively the same objects. And these objects are now more supercharged and powerful than they ever were in either of our packages before. They're bundling kind of all the information that we think is useful for you in the context of an explanation. So you'll get things like what were the original feature names, what was the underlying data for the explanation, what are the attribution values that were learned, and perhaps more importantly, you can kind of slice them in intuitive kind of Pythonic ways. If you just want the explanation for one instance, even though you computed it for 100, you can kind of slice it off naturally. And if you just want to look at the explanations across a few instances for a couple of different features, again, it all kind of follows these like nice Pythonic slicing paradigms. Perhaps even more importantly, if you like the visualizations you see from the SHAP package, but you used an interpretable ML model, you can just pass that explanation straight to SHAP and start getting Scott's waterfall plots or anything you like in the SHAP package. And vice versa, you can do the same from taking SHAP explanations. If you want that kind of interactivity that you saw in Interpret ML, you can just compute things with SHAP and pass it right back to us. It's really kind of a cohesive experience. One last thing I want to call out, because these objects are so, they can encapsulate all the information we think you need, it's also really easy to build your own plots off of them. So with just 20 lines of code, a lot of it is just formatted, right? I can take any explanation, whether it's produced by SHAP or Interpret or any of the other packages that are starting to adopt this API, and produce my own graphs using a framework like Plotly. Perhaps even cooler, I can also, with just a couple more lines of JavaScript and HTML, I can start building my own dashboards. You know, maybe I want to build my own comparison experience or embed it inside of an enterprise dashboard that I'm using. Now that these objects are shared and simple, we're really hoping to take the interpretability ecosystem as a whole to the next level and enable people to build all kinds of cool experiences. This is just a dumb little dashboard I made in about 10 minutes for comparing what comes out of an EBM with what comes out of SHAP. But you can imagine you can do all sorts of cool new things now that the kind of foundation is laid between all the interpretability packages out there. So that's the kind of whirlwind tour of Interpret. A lot of the stuff that you've learned about Interpret is also applicable to SHAP and vice versa. These objects are now becoming very, very similar. And Scott, us, we're all excited about kind of pushing this out and seeing what kinds of new innovations can come out of the interpretability space. And with that, that's it. That's my spiel. Again, all of these notebooks can be found inside of our Interpret ML GitHub. So please check it out and reach out if you have any questions. Thanks.
That was great, Harsha. Thank you. And we're finishing almost on time, so which is good. So thank you all for joining us. And as we said, feel free to contact us if we can help you.
Thank you much. Thank you so much, Rich and Harsha, everybody here. It's been an absolute pleasure. Very enlightening, very great stuff. And Rich, very much looking forward to your talk on Thursday. So thanks everybody for joining. And yeah, we'll see everybody soon.
Great. Thank you.